On a summer morning, the Mediterranean can look almost too familiar to be mysterious. Ferries leave white wakes between Greek islands. Fishing boats return toward harbors that have been used for centuries. Along the Spanish coast, beaches fill beneath a cloudless sky. Farther east, small vessels move through the Aegean past cliffs and villages that seem to rise directly from the water. From southern France to North Africa, from Italy to the Levant, millions of people live beside this sea, travel across it, swim in it, fish from it, and look over it every day. Few bodies of water on Earth have been painted, mapped, crossed, fought over, and written about so often. Even people who have never stood on its shore recognize the shape it makes between Europe, Africa, and Asia. It seems difficult to imagine that a place this familiar could still conceal anything fundamental about itself. Yet almost everything that makes the Mediterranean extraordinary begins where the familiar view ends. From a beach, the sea looks like a surface. From above, it looks like blue space between continents. But beneath that surface is a landscape whose scale is almost impossible to judge from shore. The shallow shelf beside a coastline can suddenly give way to steep submarine slopes. Canyons cut through the seabed, some descending into water so deep that sunlight has disappeared long before the bottom is reached. Farther offshore lie broad basins separated by ridges, trenches, and underwater mountains. In the Ionian Sea, the Mediterranean descends to the Calypso Deep, more than 5 kilometers beneath the surface. A person standing beside the water in Greece can therefore be surprisingly close, geographically, to an environment more distant vertically than many mountains are high. In 2025, researchers examining the 5,112-meter deep Calypso Deep reported something that demonstrated just how connected even this remote bottom is to the world above. Human debris had already accumulated there. That depth alone changes the way the Mediterranean should be imagined. This is not a shallow bowl surrounded by beaches. It contains a genuine deep sea, and those depths are not empty. Water continues moving through them. Sediment records what happened thousands and millions of years ago. Microorganisms survive in environments with no sunlight at all. Animals descend through the darkness in search of prey. Sperm whales regularly inhabit the Mediterranean, as do fin whales, the enormous baleen whales that are among the largest animals alive. Both are recognized as regular Mediterranean species by the regional agreement responsible for cetacean conservation in these waters. Above them, container ships, ferries, fishing vessels, and pleasure boats may pass without anyone aboard realizing that a whale is moving through the black water below. The contradiction is everywhere. The Mediterranean is crowded at its edges but still contains places humans have barely observed directly. It is surrounded by some of the oldest continuously inhabited regions on Earth, yet large parts of its seabed have been explored only remotely. Its surface may be crossed in hours by aircraft, while reconstructing the history preserved beneath that surface has taken scientists generations. And the deeper researchers have looked, the less permanent this sea has begun to seem. That is perhaps the hardest idea to accept at first. A coastline gives the impression of certainty. Land ends here, water begins there. Maps strengthen the illusion by drawing the boundary as a clean line. But the Mediterranean coastline is only the present position of a boundary that has moved repeatedly through geological time. Islands have been connected to larger land masses and separated again. River valleys have been drowned. Tectonic forces have lifted mountains while lowering basins. Earthquakes have moved coastlines in moments. Volcanoes have built islands, destroyed settlements, and deposited ash hundreds of kilometers from their source. The Mediterranean sits inside a region where the African and Eurasian tectonic systems continue to interact, and the consequences are written into much of the landscape surrounding the sea. Santorini's cliffs are not merely picturesque walls around a beautiful bay. They expose part of the history of a volcanic system capable of immense eruptions. Stromboli rises from the Tyrrhenian Sea as the visible summit of a volcano whose structure continues far beneath the waterline. Etna towers above Sicily, near the meeting place of complicated tectonic processes that have shaped this region for millions of years. Around Greece, Italy, and the eastern Mediterranean, faults and subduction zones remind us that the basin is not resting on a finished piece of earth. The geography is still being made, but even that is only the uppermost layer of the story. If we could remove the Mediterranean water and then peel away the sediment covering parts of its floor, we would encounter something far stranger than ordinary rock. Beneath enormous areas of the basin lie immense deposits of evaporite minerals, gypsum and salt laid down during one of the most extreme environmental episodes in Mediterranean history. Some sequences reach extraordinary thicknesses. They are not the remains of an ordinary modern sea. They formed during a period between roughly 5.97 and 5.33 million years ago, known as the Messinian Salinity Crisis, when exchange between the Mediterranean and the Atlantic became severely restricted, and the chemistry, water balance, and landscapes of the basin changed on a scale that scientists are still working to reconstruct. The existence of those salts is one of geology's more unsettling reminders that even an entire sea can have a radically different past. For many years, the most dramatic version of the story was also the easiest to picture. The Mediterranean becomes isolated from the Atlantic. Evaporation continues beneath a hot climate. Water levels plunge, and a vast portion of the basin dries into a white desert of salt. Rivers descend through immense canyons toward isolated remnants of hypersaline water. Then, eventually, the Atlantic breaks back through and fills the basin again. Parts of that picture remain important, but the deeper scientists examine the sediments, the less useful the simple version becomes. Researchers now emphasize that the Messinian Salinity Crisis was more complicated than merely sealing a giant bathtub and waiting for it to evaporate. The amount of drawdown, its timing, differences between eastern and western basins, and the environments in which different evaporites formed remain subjects of active investigation. A major 2024 review describes Mediterranean salt giant formation as a process substantially more complicated than the straightforward evaporation of a completely enclosed sea, while recent geochemical work supports a multi-phase history in which major salt deposition occurred under changing hydrological conditions. That uncertainty does not weaken the story. It makes the evidence beneath the Mediterranean more valuable. A salt crystal can preserve information about the water from which it formed. A layer of gypsum exposed on land may represent conditions that existed around the basin millions of years ago. Sediments drilled from below the modern seafloor become pieces of a timeline. Seismic surveys allow researchers to trace buried layers across enormous distances without physically excavating them. River valleys now drowned beneath seawater record periods when their mouths lay at very different elevations. What looks from the surface like a single uninterrupted blue sea becomes, in geological data, a stack of former worlds. And those worlds sit underneath a body of water that is unusual even today. The Mediterranean is almost surrounded by land. To the north lie Europe and Anatolia. Africa forms its long southern boundary. The Levant closes much of the east. There are connections toward the Black Sea, and since the 19th century, the Suez Canal has created a direct route toward the Red Sea. But the Mediterranean's natural connection to the Great Atlantic Ocean is concentrated at its western entrance, the Strait of Gibraltar. At its narrowest, Europe and Africa are separated there by only about 14 kilometers of water. Through that relatively small gateway passes an exchange that helps determine the physical character of the entire Mediterranean. Water continually evaporates from the Mediterranean surface. The surrounding climate means that, across the basin as a whole, the loss of fresh water through evaporation is greater than the fresh water supplied by rain and rivers. If that deficit simply continued without replacement, Mediterranean water levels would fall. They do not, because Atlantic water enters through Gibraltar. Meanwhile, saltier, denser Mediterranean water eventually flows outward toward the Atlantic, below the incoming surface layer. The gateway therefore carries water in opposing directions at different depths. The consequences reach thousands of kilometers eastward. Water that enters from the Atlantic does not remain chemically identical as it crosses the sea. Evaporation concentrates salt. different water masses form, temperature and salinity influence density. Winds, coastlines, underwater topography, and seasonal changes help drive a circulation system connecting the Western Mediterranean with waters much farther east. The surface that appears motionless from a beach is therefore only the top boundary of a three-dimensional system that is continually transporting heat, salt, oxygen, nutrients, and living organisms. This makes Gibraltar more than a shipping passage. It is one of the reasons the Mediterranean exists in its present state. And it has not always functioned as it does now. That fact links the modern sea directly to those enormous salt deposits buried underneath it. The gateway between the Atlantic and Mediterranean has changed through geological time, as tectonics, erosion, and sea level altered the connections between the two water bodies. When those connections became severely restricted near the end of the Miocene, the Mediterranean entered the environmental crisis whose traces are still being studied today. When Atlantic connectivity was later restored, the basin entered another transformation just as dramatic. The sea's past is therefore not hidden in one archaeological ruin or one mysterious trench. It is distributed everywhere. It exists in minerals beneath the seabed, in the shape of drowned valleys, in volcanic islands, in active faults, and in the modern currents still passing Gibraltar. It is even carried by the animals moving through those currents. A sperm whale surfacing in Mediterranean waters seems, at first, completely unrelated to an ancient salt deposit several kilometers below the seabed, yet both belong to the same geological story. The shape and depth of modern basins influence where deep-diving whales can hunt. Those basins exist because of tectonic processes operating over millions of years. Their modern water came through gateways whose history controlled the Messinian Crisis. Biology sits on oceanography. Oceanography sits inside geology. Once those layers are seen together, the Mediterranean stops behaving like a collection of unrelated facts. Human history adds another layer. Long before satellites could map the bottom, sailors learned the Mediterranean from the surface. They did not know the depth of the Ionian basins or the thickness of Messinian salt, but they understood winds, currents, islands, and coastlines well enough to turn this sea into one of humanity's great routes of exchange. Phoenician merchants crossed it. Greek communities spread along its shores. Roman ships carried grain, wine, oil, soldiers, and information through a maritime network that helped support an empire. Countless vessels never completed those journeys. Some settled onto the seabed with their cargo still aboard, where archaeologists now use amphorae, timbers, and ordinary possessions to reconstruct economic connections erased from written history. Modern ships pass above those wrecks today, and below some of the wrecks lie sediments older than humanity. Below those sediments are geological structures formed before the Mediterranean looked anything like it does now. That is the perspective the surface hides. A person standing beside this sea may be looking over a shipping route used for thousands of years, a whale habitat, a submerged canyon, an active fault, and a geological archive reaching millions of years into the past, all occupying essentially the same patch of blue water. The Mediterranean is familiar because humans have lived beside it for so long. But familiarity has confused proximity with understanding. We know its coastlines better than almost any other sea. We have named its islands, measured its depths, crossed its channels, and built cities around its shores. Yet beneath those cities and beneath that water is evidence that the Mediterranean itself has repeatedly changed identity. To understand the sea that exists today, we therefore have to leave the present behind. Not by thousands of years, to the first sailors, not by tens of thousands, to changing Ice Age coastlines. We have to travel back nearly 6 million years to a Mediterranean whose connection with the Atlantic was failing and whose water was beginning to record that failure in layers of mineral salt. A sea bordered by landscapes no human had ever seen, entering a transformation so extreme that its effects are still buried beneath the water today. The first signs of the crisis would not have looked like the disappearance of a sea. There was no single afternoon when the Atlantic stopped arriving and the Mediterranean began draining away. The change unfolded through a narrowing relationship between two bodies of water that had exchanged freely for millions of years. By the late Miocene, the geography around the western Mediterranean was already very different from the map we know today. The modern Strait of Gibraltar did not yet exist in its present form. Instead, Atlantic water could enter through a shifting system of marine corridors across what are now southern Spain and northern Morocco. Tectonic uplift, erosion, and changing sea level gradually altered those gateways. The Mediterranean did not suddenly become a sealed basin, but its connection to the global ocean became increasingly restricted, and in a sea where evaporation already removes enormous quantities of fresh water, restriction changes everything. Around 597 million years ago, the geological record begins showing the unmistakable signs of what scientists now call the Messinian Salinity Crisis. At first, the transformation was chemical as much as geographical. The Mediterranean still contained water, but its ability to exchange that water with the Atlantic had weakened. Evaporation continued under the region's dry climate. Every molecule of water that escaped into the atmosphere left its dissolved salts behind. In an open ocean, this hardly matters because currents continually redistribute water on a planetary scale. In a restricted basin, the same process can push salinity toward extremes. Once seawater becomes concentrated enough, minerals begin to precipitate. Calcium sulfate minerals such as gypsum appear first under certain conditions. With further concentration, sodium chloride, the mineral we know as halite, ordinary rock salt, can crystallize in enormous quantities. The Mediterranean began producing not merely salt flats along a shoreline, but one of the great evaporite deposits known from Earth's recent geological history. Researchers estimate that the crisis ultimately produced close to 1 million cubic kilometers of evaporite salts, much of it now buried beneath younger sediments and the modern sea. The scale is difficult to appreciate because almost none of this salt is visible from a boat. Modern sonar and seismic surveys can look through the sedimentary layers beneath the seabed, and there the crisis appears as a vast geological structure extending across Mediterranean basins. In some places, the evaporite succession reaches hundreds of meters and locally kilometers in thickness. These are not isolated salt pans preserved by chance. Together, they form what geologists call a salt giant. The Mediterranean that millions of people cross today is sitting above the remains of a chemical transformation that affected almost the entire basin. Long before scientists understood exactly how those deposits formed, their existence posed a simple problem. Producing that much salt required extraordinary amounts of evaporation and a highly unusual water balance. Something had happened here that had no equivalent in the Mediterranean of today. Some of the first major clues came from drilling. During deep-sea scientific expeditions in the 20th century, cores recovered from beneath the Mediterranean floor revealed thick evaporites where normal marine sediments might have been expected. Later seismic surveys transformed those individual samples into something much larger. Sound waves sent through the seabed reflected differently from salt, sediment, and rock, allowing geophysicists to trace buried structures over vast distances. What emerged was not simply evidence of salty water. It was evidence that the entire hydrological character of the Mediterranean had changed. Onshore, the same interval appears in exposed gypsum formations around Spain, Italy, Sicily, Cyprus, and other parts of the basin. Offshore, kilometers of younger sediment conceal an even larger record. The crisis had left its signature almost everywhere scientists looked. Yet understanding that record has turned out to be far more difficult than telling the popular version of the story. For decades, one image dominated public imagination. The Mediterranean almost completely dries out, leaving a gigantic depression bordered by cliffs, with isolated brine lakes shimmering far below the level of the Atlantic. It is an irresistible scene. If sea level fell by more than a kilometer, rivers entering the basin would suddenly encounter a much lower destination and cut deep valleys into their existing landscapes. Evidence for major river incision does exist around the Mediterranean. The Nile, Rhone, and other river systems preserve buried erosional features that have long been interpreted as signs of dramatically lowered base level during the crisis. Some reconstructions therefore envision a Mediterranean whose surface stood hundreds of meters, perhaps more than a kilometer, beneath the Atlantic during parts of the event. Recent geochemical work has strengthened the case for a major drawdown during at least one phase, while other datasets and interpretations continue to argue for less extreme scenarios. This is where the story becomes more interesting than the simplified version. The question is no longer whether something extraordinary happened. The salt giant alone settles that. The argument is about what the Mediterranean looked like while it was happening. Some deep basin evaporites show characteristics consistent with deposition underwater rather than on an exposed salt desert. Studies of material recovered from deep Mediterranean settings have found no unequivocal evidence that all those salts formed in shallow coastal pans or completely dry basins. That means substantial bodies of water may have persisted even during severe restriction. Later stages of the crisis may have included stratified lakes or basins fed increasingly by rivers and water from neighboring regions, rather than by normal Atlantic inflow. In other words, there may never have been one single Mediterranean-wide landscape. The western basin could behave differently from the east. Deep depressions could retain water while margins were exposed. Salinity could vary dramatically between layers and through time. What people casually describe as the Mediterranean drying up was probably a sequence of changing environments spread across more than 500,000 years. That distinction matters because the Mediterranean is enormous. Even today, evaporation could not turn the entire basin into salt overnight. Restricting Atlantic inflow changes the water budget, but climate, river input, remaining gateway exchange, and the shape of individual basins all affect the outcome. Researchers now divide the Messinian Salinity Crisis into several stages rather than treating it as one uninterrupted drying event. Early evaporites appeared around basin margins. Later, enormous quantities of halite accumulated in deeper parts of the Mediterranean. Still later, environmental conditions shifted again, with evidence suggesting increased freshwater influence in parts of the basin. The crisis was not a steadily emptying bathtub. It was a hydrological system repeatedly reorganizing itself as the gateway to the Atlantic became less effective. Life responded to those changes long before the first great salt layers appeared. Fossil evidence shows that Mediterranean marine ecosystems were already being disturbed as connection to the Atlantic weakened. Normal marine organisms disappeared from some sedimentary records, while opportunistic species better suited to unusual conditions became more common. A 2024 reconstruction of the Mediterranean marine fossil record describes the crisis and the events leading to it as the greatest environmental perturbation experienced by the Mediterranean Sea, with major consequences for marine biodiversity. The water was becoming chemically and ecologically unlike the normal marine environment that had existed before. For animals unable to tolerate extreme salinity, the change could be absolute. A fish does not need the entire Mediterranean to evaporate to lose its habitat. It only needs temperature, oxygen, or salinity to move beyond the range its physiology can tolerate. Food webs can fail before shorelines disappear. Plankton communities change. Bottom-dwelling organisms vanish from environments where chemistry becomes hostile. Connections that once allowed species to move between Atlantic and Mediterranean waters narrow or disappear. The ecological Mediterranean was being dismantled long before the geological crisis reached its most dramatic phases. On land, falling water levels, whatever their exact magnitude, would also have changed the relationship between rivers and the sea. A river is constantly adjusting itself to the elevation at which it ends. Lower that endpoint substantially, and the river begins cutting downward into its own valley. This is one reason buried canyons around the Mediterranean have attracted so much attention. Beneath later sediments near the Nile and other major river systems lie deeply incised landscapes that appear to record a time when Mediterranean base level was far below the modern coastline. New seismic work beneath the Nile region, published in 2026, has added further evidence interpreted as supporting very large Messinian sea level changes, although researchers still disagree about how broadly such evidence should be applied across the whole basin. Picture the consequence without turning it into fantasy. The Nile was already an immense river system. If the Mediterranean at its mouth dropped hundreds of meters, the lower river would begin cutting aggressively through older sediments, creating a canyon where today there is a broad delta and coastal plain. Later, when normal marine conditions returned and sea level rose, those valleys would drown and gradually fill with sediment. The modern landscape would hide the evidence almost completely. Only drilling and geophysical imaging millions of years later would reveal the buried topography. The same concealment happened offshore. Once the crisis ended, ordinary marine sediments began accumulating above the evaporites. Rivers carried mud and sand into the basin. Plankton died and settled through the water column. Turbidity currents moved sediment down submarine slopes. Layer after layer covered the Messinian surface, until much of the salt giant disappeared kilometers beneath the modern seabed. Ironically, the Mediterranean eventually buried the evidence of its own transformation. Scientists therefore reconstruct the crisis like a forensic event whose scene has been repeatedly altered. A core drilled through the seabed provides only a narrow vertical sample. An outcrop in Sicily or Spain records conditions along an ancient margin, but not necessarily what was happening kilometers away in a deep basin. Seismic profiles reveal structure, but cannot always tell researchers the exact chemistry or age of a layer without supporting samples. Microfossils can reveal whether water was marine, brackish, or hostile to particular organisms. Isotopes preserved inside minerals can indicate where the water came from and how strongly it evaporated. Magnetostratigraphy and astronomical cycles help establish timing. No single piece gives the complete answer. The Mediterranean has to be reconstructed from thousands of pieces gathered across multiple countries and beneath thousands of meters of water. That is why disagreements remain after more than 50 years of intense research. One group of evidence can support kilometer-scale drawdown. Another can indicate that parts of the deep basin remained permanently submerged. Those statements are not necessarily mutually exclusive. The Mediterranean could lose an enormous amount of water without becoming completely dry. It could contain deep hypersaline lakes, hundreds or thousands of meters below former shorelines. Water could periodically enter from the Atlantic, while evaporation continued to dominate. Rivers and perhaps connections with Paratethys could freshen upper layers, while concentrated brines remained below. The closer the science gets to the actual event, the less it resembles a single dramatic postcard, and the more it resembles a rapidly changing planet-scale experiment. There is another clue hidden in the sheer quantity of salt. To deposit nearly 1 million cubic kilometers of evaporites requires more dissolved salts than one Mediterranean-sized volume of normal seawater could provide. Water had to enter, evaporate, leave its salts behind, and be replaced repeatedly. Even during severe restriction, therefore, some exchange with external waters was likely necessary during important phases of salt deposition. This is one of the reasons modern researchers describe salt giant formation as more complex than simply closing the Atlantic gateway completely. The Mediterranean could be restricted enough for evaporation to dominate, while still receiving enough saline water to continue feeding the enormous mineral factory developing on its floor. For hundreds of thousands of years, the balance shifted. Gateways rose or eroded. Climate varied. Freshwater input changed. Water levels moved. Gypsum accumulated. Halite accumulated. Ecosystems collapsed and reorganized. Rivers carved downward and later deposited sediment again. The Mediterranean had not ceased to exist, but it had ceased to behave like the Mediterranean we know. Then, close to 533 million years ago, the record changes abruptly. Above Messinian deposits across much of the basin appear sediments marking the return of normal marine conditions at the beginning of the Pliocene. Atlantic organisms could once again enter. Salinity moved back toward ordinary marine values. The Mediterranean became connected to the global ocean in a way it had not been for hundreds of thousands of years. Something had happened at the western edge, where tectonics and erosion had spent ages restricting the exchange. Atlantic water had found a route back into the basin, and once that route began to enlarge, the difference in water level between the ocean and the Mediterranean may have turned an ordinary breach into an event on a scale difficult to compare with anything humans have ever witnessed. The salt beneath the sea tells us what came before. The scar in the landscape begins to tell us what happened next. The scar begins west of the Mediterranean itself. Beneath the modern waters around Gibraltar and the Alboran Sea, geophysical surveys have revealed an immense buried erosional feature extending for hundreds of kilometers. It is difficult to reconcile with the quiet exchange that passes through the strait today. Something once moved through this landscape with enough force to excavate rock, carry enormous amounts of sediment away, and leave a channel that would later be concealed beneath millions of years of younger deposits. For researchers trying to understand how the Messinian Salinity Crisis ended, that buried landscape became one of the most important pieces of evidence. At approximately 533 million years ago, the sharp chemical and ecological disruption recorded throughout the Mediterranean gives way to the return of normal marine conditions. Atlantic organisms reappear, marine sediments spread across environments previously dominated by evaporites and unusual waters. Whatever happened, it happened at the exact place where the Mediterranean had always been most vulnerable, its connection to the Atlantic. One explanation has become known as the Zanclean Flood, and if its most dramatic reconstruction is broadly correct, the Mediterranean did not simply refill. During its final stage, it may have undergone one of the most powerful flooding events identified in Earth's geological record. The landscape at Gibraltar would have been unfamiliar. The narrow marine passage separating Spain and Morocco today is a relatively recent configuration within a region whose gateways had repeatedly shifted. Earlier in the Messinian, connections between Atlantic and Mediterranean waters had existed through corridors across southern Iberia and northern Morocco. Tectonic deformation gradually altered those routes. By the end of the Salinity Crisis, the Mediterranean may have stood substantially below the Atlantic, although, as we have already seen, the exact difference remains disputed. That difference in elevation is crucial. Water always responds to gravity. Give an ocean access to a lower basin, and even a modest initial flow can begin changing the terrain through which it travels. What starts as leakage can become erosion. Erosion deepens the channel. A deeper channel admits more water. More water produces more erosion. Under the right conditions, the process feeds itself. This positive feedback is the heart of the Zanclean flood hypothesis. Atlantic water is thought to have found a path across the Gibraltar region and begun flowing eastward toward the lower Mediterranean. At first, that flow may have been relatively modest, but water traveling downhill carries energy, and moving water is exceptionally good at reshaping landscapes. Loose sediment is swept away first, then the channel cuts deeper into bedrock. As its cross-sectional area increases, still greater quantities of water can pass through. The discharge rises, increasing erosion yet again. A threshold can eventually be crossed, where the system no longer behaves like a river, gradually carving a valley. It becomes an outburst flood whose own force is enlarging the route that feeds it. That mechanism is not invented simply to make an ancient event sound dramatic. It emerged from attempts to explain the physical dimensions of the erosion preserved below the western Mediterranean. Seismic imaging has identified a deeply incised channel running from the Strait of Gibraltar into the Alboran Sea, in places buried beneath later sediments. Reviews of the Gibraltar region describe this erosional feature as reaching roughly 390 kilometers from the Gulf of Cadiz toward the Algerian basin, and being hundreds of meters deep in places. Something had to excavate it. The scale, orientation, and age of the feature helped drive the idea that the Mediterranean's reconnection involved a powerful inflow from the Atlantic, rather than only a slow marine transgression spreading quietly across the basin. In 2009, researchers attempted to go further. Instead of asking only whether a flood occurred, they modeled how the landscape and water would interact if Atlantic water began cutting through Gibraltar into a Mediterranean standing far below ocean level. Their calculations produced an event almost beyond intuitive scale. In the model, erosion accelerated the flow until peak discharge reached on the order of 100 million cubic meters of water per second. That would be roughly 1,000 times the discharge of the modern Amazon River. The authors estimated that during peak conditions the Mediterranean could have risen by more than 10 meters in a single day, and that the final, dominant phase of refilling could have supplied around 90% of the incoming water in a period ranging from several months to about 2 years. These are not measurements from 533 million years ago. They are model results dependent on assumptions about the amount of prior drawdown, rock erodibility, and the geometry of the gateway. But they reveal what the surviving landscape can imply if those assumptions are approximately right. The word flood almost becomes inadequate at those scales. Human experience usually involves water moving across a landscape whose basic geography remains intact. Here, the water itself may have been creating the geography through which it traveled. At the western entrance, flow would have rushed down an enormous gradient toward the lower basin. The faster it moved, the more rock and sediment it could remove. What happened downstream would have depended on the topography of a Mediterranean very different from today's. Water entering the western basin first had to spread through that depression. The connection farther east was complicated by the higher terrain around Sicily, which separates the western and eastern Mediterranean basins even now. This became important because the eastern Mediterranean appears to preserve evidence of another stage in the event. Research around the Sicily Channel and Malta escarpment has identified extraordinary erosional landforms and sedimentary deposits that have been interpreted as the path of water spilling from the already refilling western Mediterranean into an eastern basin that may still have stood much lower. In one reconstruction, water first raised the western Mediterranean until it overtopped the barrier toward the east. The flow then accelerated down the escarpment, carving channels and transporting vast quantities of debris. Evidence reported from Sicily includes streamlined terrain, large eroded ridges, and sediment bodies whose distribution is consistent with a powerful eastward flood. A 2024 study brought terrestrial and offshore observations together and argued that these features provide a connected land-to-sea record consistent with the Zanclean megaflood extending into the eastern Mediterranean. This possibility makes the refilling much more complex than the image of an Atlantic waterfall pouring into one empty hole. The Mediterranean consists of multiple basins separated by ridges and sills. If their water levels differed, the flood could have progressed in stages. The western basin might rise first. Water might then find or overtop another low point. A second major cascade could develop farther east. Valleys, slopes, and remaining bodies of water would all influence the direction and violence of the flow. Even if the total event was geologically brief, it may have contained distinct phases that looked very different from one another. Nor should we imagine an exposed Mediterranean basin with modern coastlines simply shifted downward. Millions of years of erosion and sedimentation have changed the topography since then. Areas that are deep today were not necessarily shaped exactly the same way. Sediments later buried some of the flood's scars. Tectonic deformation moved parts of the crust. Isostatic adjustment altered elevations as enormous masses of water and sediment were removed or restored. Reconstructing the event, therefore, means correcting for everything that happened after it, then asking what landscape could have produced the structures that remain. That is why there is still debate. The catastrophic refilling model is supported by remarkable geomorphological and seismic evidence, but the magnitude of the flood depends heavily on how far the Mediterranean had fallen before Atlantic water returned. Some studies favor kilometer-scale drawdown, others reconstruct considerably smaller drops. A 2022 analysis of the Messinian Nile system, for example, argued for a much more limited sea level fall than the most extreme traditional estimates. If the initial difference between Atlantic and Mediterranean water levels was smaller, the potential energy available to drive the flood would also have been smaller. Researchers also continue discussing whether Atlantic exchange had completely stopped before the final reconnection, or whether restricted inflow persisted during parts of the crisis. There is also a question of timing. Geology can identify an abrupt boundary without necessarily telling us whether the transition took months, decades, or centuries. A layer only centimeters thick may represent a surprisingly long interval. An erosional surface may represent missing time rather than instantaneous change. Numerical modeling helps narrow possibilities, but it cannot replace observations. Computational fluid dynamics studies have produced alternative estimates for the flood's duration and magnitude depending on the assumed gateway and basin geometry. The broad picture of rapid Atlantic reconnection is compelling. The exact speed of that reconnection remains one of the reasons the Zanclean event continues attracting scientific attention. What makes the story powerful is that none of this uncertainty changes the transformation recorded throughout the Mediterranean at the Miocene-Pliocene boundary. Before it, the basin contained the extraordinary evaporitic environments of the Messinian Crisis. Immediately afterward, marine conditions returned across an enormous region. Organisms with Atlantic affinities recolonized Mediterranean waters. Normal marine sedimentation resumed. The giant salt-producing system stopped. The transition is so important that approximately 5.33 million years ago marks not merely the end of the Messinian Age, but the beginning of the Zanclean Age of the Pliocene. For life, the change was almost equivalent to the creation of a new sea. The Mediterranean after reconnection was not populated simply by whatever organisms had survived the crisis. Atlantic species gained access through the reopened Western Gateway. Marine communities began rebuilding, but repopulation was not instantaneous. Research from the Alboran region indicates an ecological recovery unfolding after Atlantic waters returned, with bottom environments and marine circulation taking time to stabilize. A physical connection can be restored much faster than an ecosystem can reconstruct itself. Sediment began covering the scars of the crisis. New marine muds settled onto old evaporites. River systems adjusted to a higher base level. Valleys in size during low water phases became drowned and eventually filled. The extreme brines and exposed margins disappeared beneath ordinary seawater. Over millions of years, the evidence of the event became increasingly difficult to see from the surface. Gibraltar narrowed into the recognizable gateway of today. The Western Mediterranean acquired its modern water depths. Later tectonic movements continued reshaping the eastern basin. Eventually, humans appeared along shores that carried almost no visible reminder of what had happened there. And yet the event never completely disappeared. Its channel survives beneath younger sediments near Gibraltar. Its possible flood deposits remain along the route into the eastern Mediterranean. Its ending can be traced in cores where Messinian deposits give way to Pliocene marine sediment. The salt giant produced during the preceding crisis remains buried beneath much of the modern seabed. The Mediterranean contains, layer upon layer, both the evidence of losing its normal connection to the ocean and the evidence of getting it back. There is something particularly strange about standing at Gibraltar with that history in mind. On a clear day, Spain and Morocco can be seen across the water from one another. Cargo ships move through one of the world's busiest maritime passages. Dolphins and whales cross between Atlantic and Mediterranean habitats. To anyone watching from shore, the strait appears simply to be a narrow section of sea between two continents. But beneath those ships lies the descendant of a gateway that once controlled the fate of the entire Mediterranean. The spectacular phase of refilling eventually ended because the difference in water level disappeared. Once the Mediterranean rose toward Atlantic level, gravity no longer had an enormous drop to exploit. The torrent weakened, erosion slowed. What may have been a geological catastrophe transformed into something much quieter. Water continued crossing Gibraltar. It still does. Every second of every day, Atlantic water passes eastward through the same region where researchers believe the Zanclean reconnection occurred. But unlike the one-directional flood imagined for 5.33 million years ago, the modern exchange contains another current moving the opposite way beneath it. The Mediterranean is still losing water to evaporation, still receiving Atlantic replacement water, still concentrating salt, and still returning dense water toward the ocean. The ancient gateway that once may have refilled an entire basin has become the narrow valve regulating the sea we recognize today. And to understand why the Mediterranean has not begun another slow journey towards salt and isolation, we have to follow that modern Atlantic water through the strait and see what happens to it once it enters. The torrent that may have accompanied the Mediterranean's return eventually disappeared because the imbalance that powered it disappeared with it. As the basin filled, the difference between Atlantic and Mediterranean water levels diminished, the enormous gravitational advantage weakened, and Gibraltar ceased to behave like the entrance to a catastrophic flood. But the movement of water never ended. More than 5 million years later, the Western Gateway is still doing something essential to the existence of the sea. The difference is that today, the process is quiet enough to cross without noticing. A ferry traveling between Spain and Morocco can pass over one current moving east, while, hundreds of meters below, another body of water moves west. From the deck, there is no line marking the boundary, no permanent disturbance on the surface, nothing that suggests two different branches of a circulation system are passing one another beneath the ship. Yet, this layered exchange is one of the fundamental reasons the Mediterranean remains the sea it is today. The Strait of Gibraltar is a remarkably small opening for such a large responsibility. It extends for roughly 60 kilometers between the Atlantic and the Alboran Sea, averages only about 20 kilometers across, and contracts to roughly 14 kilometers at the Tarifa Narrows. Its bottom is not a smooth channel. Submarine ridges and sills rise across the passage, forcing deep water over obstacles such as Cameronal Sill, where the controlling depth is only about 290 meters. Farther west lies Espartel Sill, another important restriction. To ships, these structures are invisible. To the water, they are gates within the gate, shaping how Atlantic and Mediterranean waters accelerate, mix, and pass one another. What drives the exchange begins hundreds or even thousands of kilometers away from Gibraltar, under the Mediterranean sun. Every day, water molecules escape from the surface into the atmosphere. Rain returns some of that fresh water. Rivers return more. Water also arrives through the Black Sea system, but taken across the Mediterranean as a whole, those sources do not fully replace what evaporation removes. Oceanographers therefore describe the Mediterranean as an evaporative basin with a negative freshwater balance. Evaporation exceeds precipitation and river input. The missing water has to come from somewhere. In the modern Mediterranean, much of that deficit is compensated by the Atlantic. This creates a useful thought experiment. Imagine Gibraltar closing again, not necessarily repeating the Messinian crisis, but simply eliminating the modern Atlantic exchange. Evaporation would continue, rivers would continue flowing, rain would still fall. Yet those freshwater sources would not be sufficient to maintain the present balance. The Mediterranean would begin changing. Its water budget would become increasingly negative, and as fresh water was preferentially removed through evaporation, the salts dissolved in the remaining seawater would become more concentrated. The ancient evaporites beneath the seabed suddenly stop looking like a disconnected geological curiosity. The same fundamental imbalance still exists. What has changed is that Gibraltar now continuously compensates for it. At the surface, relatively fresher Atlantic water enters the strait and flows eastward. Once inside the Mediterranean, it does not simply spread evenly through the basin. Earth's rotation, coastlines, winds, and underwater topography organize it into currents, eddies, and gyres. In the western Mediterranean, much of the incoming water follows the North African margin as the Algerian current. The current itself is unstable, generating large meanders and eddies capable of redistributing Atlantic origin water away from the coast. From there, branches continue through a sea divided by islands, channels, and submerged ridges, each modifying the route. The farther that Atlantic water travels, the less Atlantic it becomes. Evaporation is continually removing fresh water from its surface. Salt does not evaporate with it. The remaining water becomes progressively more saline, particularly toward the eastern Mediterranean, where surface salinities can exceed 39. Temperature changes as well, responding to season, latitude, and exchanges with the atmosphere. A parcel that entered near Gibraltar as relatively fresh Atlantic water may eventually arrive in the eastern basin warmer, saltier, and denser than when its journey began. The Mediterranean is effectively processing the water supplied to it. One of the most important transformations occurs in the Levantine basin of the eastern Mediterranean. During winter, the atmosphere can cool the salty surface waters. Cooling increases density. Under suitable conditions, convection and mixing drive this water downward, creating what oceanographers call Levantine intermediate water. The name sounds technical, but the process is central to the Mediterranean's circulation. This is not simply surface water that happens to sink. Levantine intermediate water is one of the major water masses manufactured inside the Mediterranean itself. Relatively warm, conspicuously saline water occupying intermediate depths, often several hundred meters below the surface. From its formation region in the east, it begins a long journey back toward the west. The Mediterranean therefore contains a kind of vertical geography invisible on an ordinary map. A political map divides the sea into countries. A bathymetric map divides it into basins and ridges. An oceanographer sees another landscape again, layers and bodies of water identified by temperature, salinity, density, and origin. Atlantic water occupies much of the upper circulation. Levantine intermediate water spreads westward beneath it. Deeper waters form in regions including the Adriatic, Aegean, and northwestern Mediterranean under particular winter conditions. These water masses mix, interact, and occasionally undergo substantial reorganizations. The Mediterranean is not one homogeneous reservoir, it is a stack of moving histories. The Sicily Channel makes that especially clear. Between Sicily and North Africa, shallow underwater topography separates the western and eastern Mediterranean at depth. Surface and intermediate waters can pass between the two, but the restriction helps make the deepest circulations of the eastern and western basins partly independent. Water formed in one region may therefore carry a recognizable chemical and physical signature across large distances before mixing erases it. Oceanographers can use those signatures almost like tracers, identifying where a body of water originated and following its route through the basin. Eventually, some of the water transformed inside the Mediterranean reaches Gibraltar again, but now it is traveling in the opposite direction. Beneath the eastward flowing Atlantic layer, saltier Mediterranean water moves west toward the ocean. In simplified form, the strait operates as a two-layer exchange. Atlantic water enters above, Mediterranean outflow water leaves below, generally beneath roughly 150 meters. The actual flow is much messier than two perfectly separated conveyor belts. Tides shift the interface, turbulence mixes the layers. Different Mediterranean water masses contribute to the outflow in changing proportions. But the underlying pattern is remarkably persistent. At the same narrow passage, the Mediterranean simultaneously receives the water it needs and exports the water it has transformed. That means a vertical line through the strait can cross water traveling toward two different oceans. Near the surface, the journey points east. Deeper down, it points west, and the two streams do not pass politely. As dense Mediterranean water approaches the underwater ridges of Gibraltar, it is forced over and around them. At Camarinal Sill, the outflow can behave like a submerged gravity current, accelerating as it crosses the topography. Tides periodically alter the strength and structure of both layers. Large internal waves form not on the sea surface but along the density boundary between them. These waves can be tens of meters high within the water column, while ships above experience nothing comparable. They propagate away from the strait, sometimes becoming visible from satellites only because they subtly alter surface roughness. Beneath that faint signature is a wave moving through an internal boundary between water masses. Recent experiments have shown just how complicated this apparently simple gateway can be. In 2026, researchers reported results from a large-scale physical model of the strait, designed to reproduce its real topography, tides, density layering, and Earth's rotational effects. The experiments highlighted the importance of turbulence generated where the Mediterranean outflow interacts with the seabed, particularly around Camarinal Sill. Instead of mixing being controlled only by shear between the upper and lower water masses, bottom-generated turbulence can play a major role in detaching and diluting the Mediterranean plume as it spills westward. Even after generations of measurements in one of the most heavily traveled straits on Earth, scientists are still refining how this exchange actually works. Once the dense Mediterranean water escapes Gibraltar, it does not simply sink to the bottom of the Atlantic. It descends along the continental slope in the Gulf of Cadiz, mixing with Atlantic water as it goes. This produces a distinctive, warm, salty Mediterranean influence at intermediate depths in the North Atlantic. The Mediterranean is therefore not merely a recipient of ocean water. It modifies Atlantic water and sends a transformed version back out, carrying a salinity signature detectable far beyond the strait. Levantine intermediate water forms an important component of that export, together with deep waters produced in the Western Mediterranean. Inside the basin, this overturning circulation has consequences far beyond salinity. When surface waters sink, they carry dissolved oxygen away from contact with the atmosphere and into deeper layers. When deeper waters are renewed, organisms living far below sunlight receive oxygen that ultimately entered the sea at the surface. Circulation redistributes heat. It transports larvae and plankton. It moves nutrients between regions and depths. It influences where biological productivity can occur and where deep environments become starved of food. The movements of whales, tuna, and countless smaller organisms take place inside this shifting physical architecture. The Mediterranean's famous clear blue water is partly connected to this story as well. Much of the open Mediterranean, particularly toward the east, is oligotrophic, relatively poor in nutrients such as phosphorus and nitrogen, available to support phytoplankton growth. Low concentrations of microscopic plant life allow sunlight to penetrate exceptionally clear water, producing the intense blue associated with Mediterranean islands and offshore waters. What looks like tropical abundance from a beach can therefore conceal a relatively nutrient-poor open sea. The Eastern Mediterranean is especially extreme in this respect. Its beauty and its scarcity are, in part, two views of the same water. That scarcity helps explain why circulation matters so much biologically. Nutrients are not evenly distributed. Rivers, coastal upwelling, vertical mixing, atmospheric dust and exchanges between water layers create local differences. Productive zones can exist beside much poorer offshore waters. Submarine canyons can funnel material into deeper habitats. Eddies can trap or redistribute plankton. Winter mixing can bring deeper nutrients toward the illuminated surface. The Mediterranean's ecosystems are built not simply on how much nutrient exists, but on where moving water carries it and when it becomes available, and the circulation itself is not fixed. Severe winters can increase dense water formation. Changes in winds alter currents. Freshwater input varies. Long-term changes in temperature and salinity can modify the properties of water masses. During the 20th and 21st centuries, oceanographers have documented major shifts in Mediterranean deep water characteristics, including episodes in which the principal sources of eastern deep water reorganized. This is one reason researchers sometimes describe the Mediterranean as a natural laboratory for studying thermohaline circulation. It contains many processes found in the global ocean, compressed into a smaller basin where changes can occur on comparatively accessible scales. It is tempting to describe the entire system as a conveyor belt. Atlantic water enters, crosses eastward, becomes salty, sinks and returns west. That picture is useful, but only as a beginning. Real Mediterranean circulation contains loops inside loops. Water can spend years circulating through gyres. Eddies pinch away from boundary currents. Intermediate water mixes with deep water. Some surface water sinks, some does not. Different regions manufacture dense water under different atmospheric conditions. The Sicily Channel filters exchanges between major basins. Gibraltar itself changes with tides on the scale of hours. The Mediterranean functions less like one conveyor and more like an interconnected network whose branches are constantly adjusting while maintaining an overall exchange with the Atlantic. Seen this way, the Strait of Gibraltar becomes the modern counterpart to the geological story beneath it. 5 million years ago, changing connections at the Western Gateway helped transform the entire Mediterranean. Today, the same narrow region still regulates a basin almost 4,000 kilometers long. The difference between crisis and stability is not that evaporation stopped or that salt ceased to accumulate in seawater. Those processes continue. Stability comes from exchange. But currents alone cannot explain why the Mediterranean has this particular shape, why one basin is separated from another, why deep trenches lie beside island arcs, or why some of the same coastlines supplied by this circulation are periodically shaken by earthquakes and overshadowed by volcanoes. Following Atlantic water eastward eventually brings us to a deeper force beneath the circulation itself. The currents are moving through a container that is still being deformed. Africa continues to converge with Eurasia. Oceanic crust is being consumed in some places, stretched or fractured in others. Islands rise where geological systems intersect the surface. Trenches descend where one part of Earth's crust bends beneath another. The water is constantly moving, and so is the ground beneath it. The ground beneath that moving water is not a single plate with a neat boundary drawn across it. It is the remains of a much older geological world being compressed, stretched, fractured, and recycled. The Mediterranean exists where Africa has been moving toward Eurasia for tens of millions of years, part of a convergence that helped consume the ancient Tethys Ocean and build mountain systems from southern Europe to western Asia. Today, the relative motion is slow enough to be invisible to anyone standing on a Mediterranean beach, only a few millimeters per year in parts of the west and around 10 millimeters per year in parts of the east. But geology does not need speed when it has millions of years. Millimeter by millimeter, ocean floor disappears beneath other pieces of crust. Rock folds into mountains, faults accumulate strain, and entire fragments of the region move relative to one another. The Mediterranean is what remains inside that unfinished collision. Calling it simply a collision between Africa and Europe, however, hides most of what makes the region interesting. There is no single continuous fault running from Gibraltar to Turkey. Some areas are being compressed, others are stretching, some boundaries slide sideways, small blocks of crust rotate or move independently between larger plates. In the east, the Anatolian region is being displaced westward, while the African plate descends beneath parts of the Aegean system. Around Italy, the geometry changes again. Old oceanic lithosphere sinks beneath the Calabrian arc, while the crust behind the subduction zone has been stretched, helping create the Tyrrhenian Sea. The modern Mediterranean is therefore not simply a depression caught between continents. Its individual seas, mountain chains, and islands are products of different parts of the same enormous tectonic reorganization. One of the clearest places to see this is southern Greece. South of Crete, the Mediterranean floor bends downward along the Hellenic subduction zone as African lithosphere descends beneath the Aegean region. On a map of earthquake locations, the boundary becomes visible not as a line on the surface, but as a belt of seismicity extending through the crust and into the mantle. The Hellenic region is among the most seismically active parts of the Mediterranean. Farther north, meanwhile, the Aegean crust is being stretched. The result is a landscape of deep marine trenches, fault-bounded basins, and island arcs arranged above a slab of lithosphere disappearing into Earth's interior. The volcanic arc sits farther north of the trench. It includes islands whose names are better known for white villages and summer holidays than for plate tectonics. Santorini is one of them. Seen from above, Santorini almost advertises what happened there. The inhabited islands form portions of a broken ring around a flooded central basin. Steep cliffs expose layer after layer of volcanic material, while the dark islands of Kameni rise near the center. This is not an ordinary bay that happened to acquire a volcano. It is a caldera system built by repeated episodes of volcanic construction and collapse. Smithsonian records identify at least 4 overlapping calderas in Santorini's history, with the youngest formed during the enormous Late Bronze Age eruption, roughly 3,600 years ago. That eruption is often introduced through the civilization living around it. The settlement at Akrotiri on Santorini was buried beneath volcanic material, preserving buildings, pottery and wall paintings with extraordinary detail. The eruption produced towering columns of ash and pumice, pyroclastic flows, and major changes to the volcanic landscape. Tsunamis generated during the eruptive sequence reached other Aegean shores. For a society dependent on ships, ports, and coastal settlements, an eruption in the middle of the sea could spread disruption far beyond the volcano itself. But this is also where a good geological story has to resist a tempting shortcut. Santorini is frequently presented as the eruption that simply destroyed the Minoan civilization on Crete. The evidence does not support such a clean cause and effect story. The eruption clearly affected the region, but Minoan society did not vanish on the day Santorini erupted, and researchers have spent decades debating how volcanic damage, earthquakes, economic disruption, and later political changes interacted. Even studies linking destruction layers on Crete to the period have distinguished seismic effects from direct ashfall. The more revealing point is that the same geological system producing spectacular islands could repeatedly intrude into human history. Santorini did not become extinct after its Bronze Age eruption. New volcanic islands began growing inside the caldera in historical times. Lava constructed parts of Palea Kameni and Nea Kameni through repeated eruptions. The most recent eruption occurred in 1950. The postcard landscape is therefore a frame taken from the middle of an active geological sequence, not a monument to something that finished thousands of years ago. Travel west from the Aegean into the waters around southern Italy, and the surface expression changes, but the deeper theme remains. Stromboli rises almost directly from the Tyrrhenian Sea. What visitors see as an island is only the upper portion of a much larger volcanic structure, extending beneath the water. For centuries, sailors crossing these waters could see incandescent explosions from its summit at night. Classical sources described its activity, and the volcano became so famous for its repeated small explosions that an entire eruptive style, Strombolian activity, was named after it. Its persistence can create a dangerous impression of predictability. Stromboli often produces relatively modest explosions, separated by short intervals, throwing glowing fragments above its craters. But ordinary activity can be interrupted by far more violent major explosions or paroxysms. ING monitoring has documented this distinction repeatedly, including intense episodes in recent years. The volcano also has an unstable northwestern flank, known as the Sierra del Fuoco, a great depression descending from the summit toward and beneath the sea. Geological evidence indicates that sector collapses have occurred in the past. Some generated tsunamis. Medieval tsunami deposits found around the island preserve episodes in which volcanic activity, landsliding, and the surrounding Mediterranean became part of the same hazard. This is an important feature of Mediterranean geology. The shoreline does not separate volcanic processes from marine ones. A collapse above water can continue beneath it. A submarine landslide can displace seawater. An earthquake beneath the seabed can move an enormous area of ocean floor almost instantaneously. The Mediterranean does not need a storm to produce a destructive wave. The event of 21 July, AD 365, demonstrates that on a scale difficult to forget. Something ruptured near western Crete with extraordinary force. Geological evidence preserved along the coast shows that parts of western Crete were suddenly lifted by as much as roughly 10 meters. Ancient shorelines that had formed at sea level were left stranded high above the water. Researchers have used radiocarbon dating of uplifted marine organisms, fault geometry, and historical accounts to connect this deformation with an earthquake estimated in some studies at around magnitude 8 or greater. Moving the crust vertically beneath an ocean moves the water above it. A tsunami spread outward. Historical descriptions record severe destruction around the eastern Mediterranean, including Alexandria. Later geological studies have found evidence consistent with the event across a much wider region, including deep-sea deposits and coastal records in North Africa. Research published in 2024 identified tsunami deposits in Tunisia that the authors correlate with the AD 365 Crete earthquake, more than 1,000 kilometers from the likely source. Imagine what that means geographically. A rupture near Crete alters the seafloor. The disturbance does not remain Greek. Long tsunami waves travel across open water at tremendous speed, almost unnoticed offshore, because their height may be modest relative to their enormous wavelength. Approaching shallower coastlines, they slow, compress, and can rise dramatically. Communities separated by hundreds of kilometers of sea can therefore experience the consequences of the same few minutes of tectonic movement. And the Mediterranean itself preserves what happened. Earthquakes can destabilize sediment sitting on submarine slopes. That material cascades downslope as turbidity currents, spreading sediment across deep basins. Researchers studying unusually thick Mediterranean deposits, sometimes called megaturbidites, have linked one widespread layer to the AD 365 event. The earthquake shook cities. The tsunami entered historical records, but beneath the sea, the event also wrote itself into sediment. Nearly 17 centuries later, cores taken from the seabed can still contain part of the aftermath. That ability to preserve catastrophe is one reason the Mediterranean seafloor matters so much. Written history around the basin extends back unusually far, allowing geologists to compare physical deposits with human accounts. A tsunami layer can sometimes be placed beside descriptions written by people who witnessed the destruction. Ancient harbor structures can reveal changes in relative sea level. Uplifted marine terraces can record earthquakes older than surviving texts. Archaeology and geology overlap because Mediterranean societies repeatedly built their cities directly beside an active plate boundary. Italy provides perhaps the most famous example. Vesuvius rises beside a region that has been densely inhabited for thousands of years. In AD 79, its eruption buried Pompeii and Herculaneum, preserving a catastrophe in such detail that individual rooms, streets, and human victims became part of the archaeological record. But Vesuvius is not an isolated chimney standing above an otherwise quiet landscape. Southern Italy sits within a much larger system created by subduction, crustal extension, and magma generation. Nearby Campi Flegrei is a vast caldera rather than a classic cone. Across the Tyrrhenian Sea, the Aeolian volcanic arc continues through islands including Stromboli and Vulcano. Etna adds another variation. Rising more than 3 kilometers above Sicily, it is Europe's largest active volcano by area and one of its most persistently active. Its exact magmatic plumbing reflects the complicated tectonic environment around eastern Sicily, near the transition between the converging African and Eurasian domains and the retreating Ionian slab. Lava flows, summit eruptions, flank vents and earthquakes are different surface expressions of a system extending deep beneath the island. But some Mediterranean volcanoes never reach the surface at all. Beneath the Tyrrhenian Sea lie volcanic structures larger than many mountains visible on land. Marsilli, for example, is an enormous submarine volcano rising thousands of meters from the seabed while remaining hidden beneath hundreds of meters of water. Around the Aeolian Islands and Aegean, additional volcanic cones, hydrothermal systems, and submerged calderas continue below sea level. Near Santorini, the submarine volcano Colombo sits northeast of the main island. Its violent eruption in 1650 breached the surface, produced ash and deadly gases, and generated a tsunami, yet today most travelers sailing nearby would see no mountain at all. This hidden geography is why monitoring the Mediterranean requires far more than watching volcanic summits. Seismometers record tiny earthquakes that can reveal magma movement or fault activity. GPS instruments measure changes in the ground on the scale of millimeters. Satellites detect deformation over broad regions. Gas instruments sample volcanic emissions. Tide gauges and offshore sensors can detect unusual changes in sea level. Sonar maps faults and landslide scars that disappear beneath the water. Researchers are effectively listening to a landscape whose most important machinery is inaccessible to direct observation. And despite all that technology, prediction has limits. Scientists can identify where earthquake hazard is high, measure strain, and improve estimates of likely scenarios, but they cannot reliably state the exact day and place a major tectonic earthquake will occur. Volcanoes can sometimes provide more immediate warning through changing seismicity, deformation, or gas emissions. Yet individual explosive events may still occur with limited warning. Stromboli is an especially useful reminder. Its ordinary explosions are familiar enough to have given their name to an eruption style, while stronger explosions can be sudden and dangerous. Monitoring does not make an active landscape inactive. It gives people a better chance of understanding what that landscape is doing. That changes how the entire Mediterranean coastline looks. The Greek islands are not scattered randomly across blue water. Some trace arcs and fragments produced by tectonic processes. The great depths south of Greece are not simply holes in the seabed. They lie beside a zone where lithosphere bends downward into Earth's interior. Santorini's caldera is not merely a perfect natural harbour. Stromboli is not simply a steep island. The mountains around the basin, the earthquakes beneath cities, the volcanoes rising from Sicily, and the trenches disappearing into darkness are different consequences of a region that has never finished reorganizing itself. Even the Mediterranean's earlier disappearance and return now fits into the same larger picture. The gateways whose restriction helped create the Messinian Salinity Crisis were altered by tectonic processes. The basin that received the Zanclean flood existed because geological forces had created depressions capable of holding kilometers of water. Gibraltar regulates the modern circulation, but the shape of every current is ultimately constrained by ridges, channels, and basins produced by the crust below. Water tells only half the story. The container itself is moving, and nowhere is that easier to forget than at the surface. A boat can drift through calm water above a fault capable of producing a major earthquake. Tourists can sleep on the rim of a volcanic caldera. A whale can dive beside a submarine canyon carved into an active tectonic margin. Ancient wrecks can settle onto sediments that will one day be disturbed by another earthquake. From shore, the Mediterranean appears horizontal, a blue surface stretching toward the horizon. Geologically, it is profoundly vertical. Mountains rise thousands of meters above it. Slabs of lithosphere descend hundreds of kilometers beneath it. Volcanoes connect deep magma systems with the atmosphere. Faults rupture below the seabed, and between those extremes are trenches and canyons that lead into a Mediterranean almost completely absent from the familiar image of the sea. Some of its largest landscapes have never seen daylight. To find them, we have to leave the islands, move away from the coast, and follow the seafloor down beyond the continental shelf, beyond the last useful sunlight, into water where the pressure becomes immense and the bottom lies more than 5 kilometers beneath the surface. And this time, the Mediterranean does not become stranger by traveling millions of years into its past. We only have to go down. The deeper we follow that unfinished landscape, the less the Mediterranean resembles the sea people know from its coastlines. The transition begins gradually. Close to shore, sunlight can still illuminate the bottom. Rocky reefs, sand, seagrass meadows, and coastal fish occupy a world connected visibly to the land above. Farther offshore, the continental shelf begins to fall away. The angle steepens. Familiar coastal habitats disappear behind us. At a few hundred meters, most sunlight is gone. Beyond roughly 1,000 meters, there is no meaningful daylight at all. The water remains cold, pressure increases relentlessly, and every animal living here depends on energy that ultimately began somewhere else. Yet the seafloor continues downward for kilometers. Along many Mediterranean margins, the route into deep water does not follow a smooth slope. Submarine canyons cut through the continental margin like valleys on land, except their walls may remain permanently dark, and their rivers are made of moving sediment rather than fresh water. Some begin surprisingly close to major coastlines. They funnel organic particles, mud, sand, and occasionally much larger debris from shallow water toward the deep basin. During powerful sediment flows, material can race downslope through these channels, carrying the biological remains of the surface world into environments that otherwise receive very little food. A canyon can therefore be both a geological scar and a supply route, connecting productive coastal waters with animals living thousands of meters below. Beyond them lie the true deep basins. Much of the Mediterranean floor sits several kilometers beneath sea level. Broad plains occupy portions of the western and eastern basins, interrupted by ridges, seamounts, trenches, and structures created by the same tectonic forces that built the islands above. The eastern Mediterranean becomes especially dramatic around the Hellenic margin. South and southwest of Greece, elongated depressions follow the complicated zone where African lithosphere is descending beneath the Aegean region. Many parts of this system exceed 3 or 4 kilometers in depth. One depression goes farther than all the others. Calypso Deep lies in the Ionian Sea within the Western Hellenic Trench system, roughly 60 kilometers from the southwestern Peloponnese. Modern measurements place its floor at approximately 5,112 meters beneath the surface. It is the deepest confirmed point in the Mediterranean Sea. 5 kilometers of water changes almost every physical condition familiar at the surface. Pressure increases by roughly 1 atmosphere for every 10 meters of descent. So near the bottom of Calypso Deep, the pressure is around 500 times atmospheric pressure at sea level. There is no sudden moment when an organism feels that pressure arrive. Deep-sea animals live with pressure inside and outside their bodies already balanced. The challenge lies in their chemistry. Proteins, cell membranes, and biological reactions must continue functioning under conditions that would disrupt the machinery of many surface organisms. Light disappears much earlier. The last sunlight capable of supporting photosynthesis is left kilometers above. There can be no seagrass here, no phytoplankton growing on the seabed, no food web powered locally by the sun. When the lights of a submersible or remotely operated vehicle sweep across the bottom, they illuminate a landscape that would otherwise remain continuously dark. Turn those lamps off and the darkness is complete. Temperature offers another surprise. The deep Mediterranean is not as cold as most of the world's abyssal ocean. Because Gibraltar's relatively shallow sill restricts the entry of the coldest Atlantic deep waters, and because Mediterranean deep waters form within the basin itself, temperatures at great depth are generally around 13 degrees Celsius rather than the near-freezing conditions typical of many deep ocean basins. That sounds comparatively mild, but it does not make the environment generous. Food remains scarce. The Mediterranean is already relatively poor in nutrients at the surface, particularly toward the east. By the time organic material has traveled several kilometers downward, much of its usable energy has already been consumed. The descent of food begins almost invisibly. Phytoplankton grow near the surface where light is available. Zooplankton eat them. Fish eat the zooplankton. Animals die. Waste particles, mucus, fragments of organisms and mineral grains stick together into what oceanographers call marine snow. It falls continuously through the water column. Most of it never reaches the abyss. Bacteria and animals consume it on the way down. Only a small fraction survives long enough to become food for the deep sea floor. That scarcity shapes almost everything that lives there. Deep sea animals often grow slowly, conserve energy, and take advantage of meals whenever they arrive. Some burrow through sediment, collecting tiny particles. Others filter the weak current. Scavengers can respond to a carcass that suddenly delivers more energy in a single event than the surrounding seafloor might normally receive over a very long period. A whale fall in the open ocean can support an entire succession of organisms. The deep Mediterranean receives fewer such enormous events, but the principle is the same. In an environment where energy is scarce, almost nothing edible is wasted. Yet some locations beneath the Mediterranean operate according to a completely different rule. The seafloor itself can provide energy. Along tectonically active margins and within thick sedimentary sequences, Fluids can escape upward from below. Methane-rich water, hydrocarbons, and other reduced chemicals emerge through cracks or porous sediments in what scientists call cold seeps. Cold only distinguishes them from hot hydrothermal vents. The fluids may still differ significantly from the surrounding seawater. In parts of the eastern Mediterranean, cold seeps occur around mud volcanoes, structures formed when pressurized fluids, gas, and fine sediment migrate upward and erupt onto the seabed. Researchers have documented specialized biological communities living around Mediterranean mud volcanoes for decades. The organisms here do not depend entirely on sunlight falling from above. Microbes can obtain energy chemically. Methane and sulfide become fuel through chemosynthesis. Some animals live in partnership with bacteria capable of exploiting these compounds. Tubeworm relatives, bivalves, and other seep-associated organisms can cluster where chemical energy emerges from the sediment. In an otherwise food-limited deep sea, a seep becomes something like an oasis, although its foundation is chemistry rather than vegetation. Mud volcanoes themselves can look deceptively familiar in sonar images. Some form cones. Others spread broad mud flows across the bottom. Gas may migrate through their sediment. Pockmarks can form where fluid escapes. In the western Alboran Basin, for example, researchers have linked active mud volcanism to deeply buried, overpressured sediments and tectonic deformation. In the eastern Mediterranean, mud volcanoes along the Mediterranean Ridge and Nile deep sea fan have provided natural laboratories for studying fluid flow, methane, and deep ecosystems. Then there are environments stranger still. In several deep eastern Mediterranean basins, exceptionally salty brines collect in seafloor depressions. These waters can become so dense that they remain separated from ordinary seawater above, creating underwater lakes with recognizable boundaries. Their origins are connected in part to the enormous evaporite deposits left by the Messinian Salinity Crisis. When deeply buried salts dissolve into fluids and reach the seabed, salinity can rise to extreme levels. From a remotely operated vehicle, the boundary of a brine pool can resemble the surface of a lake, even though it is already beneath kilometers of seawater. The denser fluid resists mixing. In some pools, oxygen is absent. Salinity and chemical conditions can be lethal to many ordinary marine animals. Yet microbial life survives at or near these interfaces, including organisms adapted to combinations of extreme salinity and oxygen deprivation that would exclude most familiar life. The geological catastrophe we encountered millions of years ago is therefore not merely preserved as buried salt. In some places, its chemistry still influences modern deep-sea environments. That connection could only be discovered once humans developed ways to see the seafloor without physically walking across it. For most of history, a sailor could measure depth with a weighted line. That revealed one number beneath one ship. Modern multi-beam sonar changes the problem completely. A research vessel sends sound pulses toward the seabed in a wide fan. By measuring how long those echoes take to return, computers reconstruct the shape of the bottom across a broad strip beneath the vessel. Pass after pass can produce detailed three-dimensional maps of canyons, trenches, landslide scars, ridges, and mud volcanoes that nobody has ever seen directly. Seismic profiling goes deeper still. Instead of mapping only the upper surface of the seabed, lower-frequency acoustic energy penetrates sediment and reflects from buried geological layers. That is how researchers can trace faults, salt bodies, and ancient sedimentary structures beneath the modern floor. But a map cannot tell us what an animal is doing beside a seep or whether a plastic bag lies among the sediment. For that, researchers send cameras down. Remotely operated vehicles remain connected to a ship by cable, allowing pilots at the surface to steer them through the darkness while transmitting video in real time. Robotic arms collect rocks, sediment, animals, and water samples. Instruments measure temperature and chemistry. Autonomous vehicles can survey wider regions without remaining physically tethered to a vessel. Deep-sea landers are lowered to the bottom and left there, sometimes for hours or days, recording currents, chemistry, or animal activity before returning to the surface. Crew-carrying submersibles remain rarer because supporting human life at extreme pressure requires an entirely different level of engineering. Calypso Deep has experienced both kinds of human exploration. A crew first reached its depths in 1965 aboard the French bathyscaphe Archimede. More than half a century later, another crewed descent in 2020 used the Deep Submergence Vehicle limiting factor. The vehicle carried cameras across part of the bottom, while researchers later studied the recorded imagery. What appeared in those images changed the meaning of the descent. At more than 5 kilometers beneath one of the world's most intensively used seas, they did not find a pristine floor isolated from human civilization. They found rubbish. A 2025 scientific analysis of imagery from Calypso Deep identified 167 objects on the seafloor. Researchers classified 148 as marine litter and another 19 as possibly anthropogenic. Most were plastics, although glass, metal, and paper were also present. The estimated density reached roughly 26,700 items per square kilometer, among the highest concentrations of litter documented in a deep-sea environment. The objects themselves were painfully ordinary: shopping bags, heavy-duty sacks, plastic cups, other pieces of packaging. Nothing about them had been designed to survive in an abyssal trench. Yet some had traveled from the world above and ended up at the deepest point of the Mediterranean. Their presence also tells us something important about how the deep sea works. Calypso Deep is not merely a hole that accidentally catches objects falling vertically from directly overhead. Currents and the topography of the trench can transport material laterally, concentrating particles and debris from a much wider region. Some litter can sink after becoming waterlogged or covered by organisms. Other material may become attached to heavier objects. Fishing and shipping can also introduce debris more directly. Whatever combination of pathways delivered each item, the trench functions partly as a collection point. That makes the discovery disturbing for a reason more subtle than the sight of plastic alone. Depth is not isolation. The same mechanisms that carry natural sediment and organic material into trenches can transport human waste. Canyons that feed deep ecosystems can also funnel pollutants. Currents connect basins biologically and chemically, but they can connect them to our discarded material as well. The deep Mediterranean is remote from human eyes, not from human influence, and even the debris becomes habitat. Researchers observed some litter partially buried in sediment, while other objects remained exposed. In the deep sea, an artificial object can provide a hard surface where the natural bottom may consist largely of soft mud. Microorganisms colonize it. Small animals may shelter beside it. Over time, the distinction between human object and marine habitat becomes physically blurred, even though the material itself remains an intrusion. Around Calypso Deep, the sediment preserves a far older record. Dust blown from continents settles here. Microfossil shells sink from the water above. Volcanic ash from eruptions around the Mediterranean can become thin chronological markers. Material transported by earthquakes and turbidity currents can leave thicker layers. Chemical changes in microscopic fossils record variations in temperature and water composition. A core only several meters long can contain a sequence of climatic and geological events spanning thousands of years. The deepest Mediterranean is therefore not empty space below the interesting part of the sea. It is an archive. It is a transport system. It contains chemical ecosystems whose energy does not begin with sunlight. It contains geological structures that connect the seafloor to processes kilometers beneath it. And it contains some of the clearest evidence that the boundary between the human Mediterranean and the natural Mediterranean has almost disappeared. Yet there is one part of this world we have only begun to follow. The lights of an ROV may reveal mud, bacterial mats, small crustaceans, or other animals close to the bottom. Above them, in the kilometers of darkness separating seabed from sunlight, other creatures are moving through water we still know largely through instruments. Some spend almost their entire lives beyond human sight. Others travel between the abyss and the atmosphere several times in a single day. A sperm whale can take a breath at the Mediterranean surface and then descend for well over a kilometre into darkness to hunt. Cuvier's beaked whales can go deeper still. Fin whales, tuna, sharks, sea turtles and monk seals use entirely different parts of the same enclosed sea. The landscape underneath the Mediterranean explains where many of them go. Now we can begin following the animals that learn to live inside it. A sperm whale at the surface gives almost no indication of where it has just been. For a few minutes, the animal breathes slowly, its blow rising at a characteristic angle from a single opening on the left side of its head. Then the back arches, the tail lifts, and several tons of living tissue disappear beneath the Mediterranean. The descent can continue for well over a kilometre, away from sunlight and into the same deep canyons and basins we have just been exploring. Down there, vision becomes increasingly useless. The whale hunts in an acoustic world, producing some of the most powerful biological sounds known, listening for echoes returning from squid and other prey in darkness. The Mediterranean population is considered distinct enough to require its own conservation attention, and many important areas for these whales coincide with steep continental slopes, submarine canyons, and deep offshore waters. The geology beneath the sea is therefore not merely scenery, it helps determine where one of the largest predators in the Mediterranean can feed. For an animal that must breathe air, this creates an extraordinary daily geography. The surface is necessary for oxygen. The deep sea is necessary for food. A sperm whale repeatedly connects the two, carrying the consequences of deep water ecology into the upper ocean every time it returns to breathe. Calves cannot accompany adults to the greatest depths at first, so groups traveling with young must balance feeding opportunities with the demands of animals still developing their diving abilities. Adults can disappear beneath the surface for long periods, hunting prey humans usually know only from nets, stomach contents, and deep-sea observations. In places such as the Hellenic Trench, the Ligurian and Tyrrhenian seas, and other steep Mediterranean margins, that behavior brings whales surprisingly close to heavily traveled coasts. A ferry passenger can be eating lunch above a submarine canyon while a sperm whale hunts more than a kilometre below. That overlap defines much of Mediterranean wildlife. Wild animals occupy a sea with unusually intense human use. Shipping routes cross feeding habitat. Fishing gear extends through migration corridors. Underwater noise travels far beyond the vessel that produced it. The Mediterranean sperm whale is listed as endangered in regional conservation planning, with threats including entanglement, ship strikes, pollution, noise, and ingestion of marine debris. The remarkable part is not simply that sperm whales live here, it is that an animal evolved for one of the most extreme hunting strategies on Earth continues to use deep Mediterranean habitat surrounded on nearly every side by people. Another whale makes that contrast even harder to ignore. Fin whales can exceed 20 meters in length, making them second in size only to blue whales. Their bodies are built for a completely different way of feeding. Instead of descending into darkness to chase individual squid, fin whales accelerate through concentrations of small prey, with their mouths open, expanding the pleated skin beneath the jaw and engulfing enormous volumes of water. Baleen then filters the prey before the water is expelled. In the western Mediterranean, especially around productive areas such as the Ligurian Provençal basin, fin whales can exploit seasonal concentrations of krill and other small organisms. The Mediterranean contains a resident fin whale population that has attracted decades of research and monitoring, although movements between Mediterranean and adjacent Atlantic waters add complexity to the picture. Their presence reveals something important about a sea often described as nutrient-poor. The Mediterranean is not equally unproductive everywhere. Circulation creates fronts. Winds drive mixing. Rivers deliver nutrients near coasts. Submarine topography alters currents. Local upwelling can bring deeper nutrient-rich water toward the surface. In the northwestern basin, winter cooling and strong winds can mix the water column deeply, helping return nutrients to illuminated layers. Phytoplankton respond. Zooplankton follow. Small pelagic fish and krill concentrate where physical conditions bring food together. A sea that appears sparse when averaged across millions of square kilometers can contain highly productive pockets capable of supporting animals weighing tens of tons. This unevenness is one of the keys to Mediterranean biodiversity. A predator does not need the entire sea to be rich. It needs to know where richness appears. Cuvier's beaked whales have taken that principle to an extraordinary extreme. They are among the deepest diving mammals ever recorded. Individuals elsewhere in the world have remained underwater for hours and descended to nearly 3 kilometers, although most dives are shallower than record extremes. Mediterranean Cuvier's beaked whales strongly associate with deep slopes and canyon systems where squid and deep-water prey are available. Records around canyon habitat in the central Mediterranean fit the same pattern. Their body plan reflects a life spent repeatedly crossing the boundary between atmosphere and abyss. Oxygen is stored efficiently in blood and muscle. The chest can tolerate enormous pressure. Metabolism is managed carefully during prolonged dives. Rather than maintaining constant visual contact with prey, these whales use echolocation clicks during the deepest hunting portion of the dive. The silence of deep water is therefore not silent at all. It contains pulses sent into darkness by animals constructing their surroundings from returning echoes. This sensitivity to sound also creates a vulnerability. Certain intense anthropogenic noises, particularly some naval sonar exposures, have been associated with atypical mass strandings of beaked whales. Conservation work in the Mediterranean treats underwater noise as a serious issue for Cuvier's beaked whales and other cetaceans. A canyon that works perfectly as feeding habitat can therefore become dangerous if the acoustic environment changes. Once again, the ecological Mediterranean and the human Mediterranean occupy the same space. Closer to shore, the animals are different, but the conflict is similar. The Mediterranean monk seal is the only pinniped resident in the Mediterranean and remains one of the world's rarest seal species. Its ancestors once occupied coastlines far more openly than many populations do today. Historical persecution and centuries of disturbance pushed surviving seals into increasingly isolated areas. In parts of the modern Mediterranean, females often give birth inside coastal caves, places protected from direct human access but vulnerable to storms, rising water, and disturbance. That behavior can give the wrong impression that monk seals are naturally animals of hidden caves. Much of their present use of caves appears to be, at least partly, a consequence of pressure from humans. A species once capable of using more open coastal habitat has been compressed into some of the least disturbed spaces remaining. Conservation successes in Greece, Turkey, and elsewhere show that populations can recover when persecution falls and breeding habitat is protected, but survival still depends on a delicate relationship with fisheries, tourism, and coastal development. A monk seal and a sperm whale seem to inhabit almost different planets. One may rest in a shallow coastal cave, the other may be hunting a squid more than a kilometer down. Yet the Mediterranean connects them through the same circulation and food web. Sea turtles make that connection across distance rather than depth. Loggerhead turtles nest on beaches throughout parts of the eastern and central Mediterranean, while the Mediterranean's major green turtle nesting areas are concentrated farther east, including Cyprus and Turkey. Yukon Regional Material recognizes loggerhead and green turtles as key Mediterranean species, alongside other marine megafauna. Hatchlings begin life crossing only a few meters of sand, but the survivors may spend years moving through pelagic waters before adopting feeding grounds far from the beaches where they emerged. Their movements make national borders almost meaningless. A turtle can hatch on one country's coast, feed in another's waters, and cross shipping or fishing zones belonging to several others during a lifetime. Some populations show remarkable fidelity to particular feeding and nesting areas. The magnetic information available through Earth's field appears to help sea turtles navigate across large distances, though they also use other sensory cues. To the turtle, the Mediterranean is not a set of countries surrounding a blue basin. It is a map of currents, temperatures, feeding habitats, and remembered destinations. Then there is an animal whose migration shaped Mediterranean economies long before scientists could track it. Atlantic bluefin tuna enter or inhabit Mediterranean waters to reproduce. Major spawning areas occur within the Mediterranean, including the waters around the Balearic Islands and other regions across the basin. ICAT research describes long-distance movement between the North Atlantic and Mediterranean and confirms the Mediterranean's central importance as a spawning region. A large bluefin tuna seems engineered around continuous motion. Its body is streamlined almost to the point of abstraction. Special adaptations allow parts of its swimming musculature and internal organs to remain warmer than the surrounding water, giving bluefin tuna exceptional performance across changing temperatures. They can cross vast ocean distances and then return towards specific spawning environments. Humans noticed those journeys thousands of years before understanding their physiology. Ancient Mediterranean societies caught tuna as they approached predictable seasonal routes. Coastal trap fisheries developed around the fact that migrating fish repeatedly passed particular points. In parts of Spain, Sicily, Sardinia, Tunisia, and elsewhere, tuna became not merely food but part of an entire maritime culture. The fish followed an ecological route. Humans built economies around intercepting it. By the late 20th century, that relationship had become dangerously efficient. Industrial fishing greatly increased the ability to locate and capture spawning aggregations, and Atlantic bluefin stocks came under severe pressure. International management through ICAT later tightened quotas and controls, contributing to substantial rebuilding compared with the crisis years. The story is important because it avoids a simplistic conclusion. Humans are capable of reducing even a powerful migratory predator, but management can also alter the trajectory when fishing mortality is brought under control. Sharks tell a less reassuring version of that history. The Mediterranean contains dozens of shark and ray species, from small bottom-dwelling cat sharks to large pelagic predators. Blue sharks cross open water. Shortfin makos, threshers, and other large species occur within or around the basin. Great white sharks have long been documented in Mediterranean waters as well, although they are rare and should not become the sensational focus of the story. The more important fact is how much these animals have declined. Regional AUKIN assessments have repeatedly identified the Mediterranean as an area of severe conservation concern for sharks, rays, and chimeras. Their biology makes them unusually vulnerable to heavy fishing. Many grow slowly, mature late, and produce relatively few young. A population cannot replace individuals as rapidly as a schooling fish releasing millions of eggs. Long lines targeting tuna and swordfish can also capture pelagic sharks. Bottom trawls encounter rays and demersal species. Some animals are retained, others become bycatch. Over generations, predators that once seemed permanent can quietly disappear from familiar fishing grounds. Removing them affects more than the species themselves. Predators influence prey behavior and abundance. Rays disturb sediments while feeding. Sharks move nutrients through food webs. The Mediterranean ecosystem is a network of these relationships, but the foundation of that network often receives the least attention because its organisms are smaller. Near the surface, everything begins with sunlight. Phytoplankton capture solar energy and carbon dioxide. They are eaten by zooplankton. Sardines, anchovies, and other small pelagic fish consume plankton and become food for tuna, dolphins, seabirds, and larger fish. Where nutrients are scarce, this chain can remain comparatively lean. Where physical processes concentrate food, abundance increases rapidly. Predators learn these patterns through evolution, experience, and migration. Closer to the bottom, another foundation appears. Posidonia oceanica is not seaweed. It is a flowering plant, complete with roots, stems, leaves, flowers, and fruits, and it is endemic to the Mediterranean. Vast meadows grow across suitable shallow seabeds. From above, a meadow may look like a dark patch beneath clear water. Ecologically, it is one of the basin's great pieces of living infrastructure. Its leaves slow water and trap particles, Rhizomes bind sediment. The three-dimensional meadow gives juvenile fish, crustaceans, and countless smaller organisms places to feed and hide. Dead leaves accumulate and decompose, feeding other parts of the coastal ecosystem. Over long periods, mats of roots, rhizomes, and trapped sediment can build beneath living plants. Some Posidonia clones can persist for extraordinary spans of time through vegetative growth, meaning a meadow may represent ecological continuity, measured not merely in years but in centuries or longer. Farther down, where insufficient light reaches seagrass, coralligenous communities build another kind of habitat. Despite the name, these are not simply coral reefs in the tropical sense. Coralline algae create hard calcareous structures that accumulate slowly, while sponges, gorgonians, bryozoans, and many other organisms add complexity. These formations are recognized as priority Mediterranean habitats because they support exceptionally diverse communities. Put all these pieces together, and the apparent contradiction begins to disappear. The Mediterranean can be nutrient-poor overall and still support whales. It can be almost enclosed and still host long-distance migrants. It can contain deep basins with very little food, while shallow meadows support dense nurseries. Its productivity is patchy rather than uniform, structured by currents, seasons, depth, and geology. Fin whales find concentrations of prey. Sperm whales use canyons. Beaked whales exploit deep slopes. Tuna cross entire basins to reproduce. Turtles connect beaches with distant feeding grounds. Monk seals search out the remaining quiet coastline. None of these animals experiences the Mediterranean as a single environment. Each follows a different version of it. And humans eventually did exactly the same thing. Long before anyone could draw an accurate map of these currents, sailors learned that particular winds returned with seasons. They learned where tuna passed, where sheltered anchorages lay, where islands appeared beyond the horizon, and where open water could shorten a journey that would take far longer by land. The ecological routes came first. Then people began turning them into human ones. Long before people could explain currents, map deep basins, or understand the tectonic forces beneath the Mediterranean, they had already learned something just as important. Water could shorten the world. A journey that might take weeks over mountains, forests, and dry interior landscapes could sometimes be completed in days by sea. Islands that looked isolated on a map became stepping stones. Natural harbors turned exposed coastlines into places where ships could wait for better winds. Straits became funnels through which people, cargo, and information repeatedly passed. The same Mediterranean that animals used as a network of feeding grounds and migration routes became, for humans, one of the greatest systems of movement ever created before the modern age. That did not happen because ancient sailors somehow conquered the sea. They learned to work within its limits. Mediterranean sailing was intensely seasonal. Winds changed through the year. Winter brought greater storm risk and fewer safe opportunities for long-distance voyages. Summer offered more predictable conditions, but even then, the sea demanded attention. A captain without satellite weather forecasts had to read clouds, swells, coastlines, and wind direction as information. Experienced sailors knew where shelter could be found if conditions deteriorated. They understood which islands could be reached before nightfall, where dangerous headlands accelerated winds, and which routes were best attempted during particular seasons. Knowledge accumulated through repetition until an apparently empty expanse of water became filled with invisible landmarks. Navigation before modern instruments was not simply a matter of steering toward a star and hoping land appeared. Much Mediterranean travel remained closely connected to recognizable coastlines, islands, and headlands, especially where geography allowed sailors to move between known points. But ancient mariners were also capable of open water passages. The position of the sun during the day, stars at night, prevailing winds, swell direction, and accumulated experience all helped maintain a course. Certain routes became familiar enough to be repeated across generations. The most valuable technology aboard a ship was therefore not always an object. It was memory. Archaeology shows that this maritime connectivity existed long before the civilizations most often associated with Mediterranean seafaring. During the Bronze Age, goods already circulated between Egypt, the Levant, Cyprus, Anatolia, the Aegean, and other parts of the Eastern Mediterranean. The distribution of ceramics and transport containers reveals exchange networks spanning hundreds of kilometers of water. Copper from Cyprus, tin obtained through wider trade systems, luxury goods, pottery, food, and raw materials moved between societies whose political borders could be very different, but whose economies were increasingly linked by ships. The Phoenicians expanded that logic dramatically during the first millennium BCE. They were not a single empire spreading outward from one capital, but a group of powerful coastal city-states in the Levant, including places such as Tyre, Sidon, and Byblos. Their home territory offered relatively little agricultural hinterland compared with large continental kingdoms, but it faced directly onto the sea. Timber from the mountains, craft production, and long experience with maritime exchange gave these communities advantages that could be transformed into trade. Tyre became one of the most important centers of Eastern Mediterranean commerce. UNESCO's description of the ancient city emphasizes the wealth and influence of merchants who navigated throughout the Mediterranean and maintained connections with settlements and colonies around its coasts. The Phoenician world eventually extended westward through commercial settlements and communities in places such as Cyprus, North Africa, Sicily, Sardinia, and the Iberian Peninsula. Carthage, founded on the North African coast, would ultimately grow into a power capable of competing with Rome for control of the Western Mediterranean. The goods themselves explain only part of why these networks mattered. Metals traveled from places where they could be mined to places where craftspeople could transform them. Wine and oil moved inside ceramic containers. Timber could become ships and buildings. Luxury materials traveled farther because their rarity increased their value. But every cargo also carried people. Merchants encountered languages they did not speak. Craftspeople saw techniques developed elsewhere. Religious practices crossed coastlines. Writing systems traveled. Local communities did not simply receive foreign objects and remain unchanged. Archaeological research increasingly emphasizes interaction, adaptation, and hybrid cultures rather than a simple picture of one civilization replacing another. The sea was creating contact zones. The Greeks followed different political patterns, but exploited the same basic Mediterranean geography. From roughly the 8th century BCE onward, Greek communities established settlements and trading centers across the Mediterranean and Black Sea worlds. Southern Italy and Sicily became so heavily settled by Greeks that later writers referred to parts of the region as Magna Graecia. Greek communities appeared along the coast of what is now southern France, including Massalia, modern Marseille, and farther west in Iberia. The Metropolitan Museum notes that these networks exchanged Greek pottery, metalwork, textiles, wine and olive oil for raw materials and luxury goods obtained elsewhere. Again, it is tempting to look at a modern map and describe this as people sailing away from Greece into foreign territory. The geography experienced by sailors was more complicated. The Mediterranean was full of intermediate points. The Aegean alone contains thousands of islands and islets. A voyage could progress from one familiar landmark to another. Sicily occupies a central position between east and west. The Strait of Messina narrows the passage between Sicily and the Italian mainland. Malta sits between Sicily and North Africa. Cyprus links the Aegean and Levantine worlds. Crete stretches across the southern Aegean like a long natural platform between Greece, Anatolia, Egypt, and the Levant. This did not make Mediterranean travel safe. It made it possible to build a system around risk. A harbor could transform a city because ships needed secure places to load, unload, repair, and wait. Geography therefore created unequal opportunities along the coast. A protected bay near productive farmland, or a river route into the interior, had advantages over an exposed shoreline with little access to inland markets. Some ports became nodes where maritime and terrestrial transport met. Goods arriving from hundreds of kilometers away by ship could then travel inland by road or river. Products from distant farms, mines, and workshops moved in the opposite direction toward the docks. The humble amphora became one of the characteristic tools of this economy. An amphora was not simply a decorative ceramic vase. Transport amphorae were standardized containers designed to move products such as wine, olive oil, fish sauces, and other commodities. Their narrow bases allowed them to be packed tightly in ships, sometimes supported against one another in organized rows. Handles made them easier to move. Different production centers developed distinctive forms. For archaeologists, that variation is invaluable. A broken amphora, discovered hundreds of kilometers from where it was manufactured, can reveal the movement of goods even when no written record survives. This means fragments of pottery scattered around Mediterranean archaeological sites effectively form an economic map. A piece of ceramic can connect a vineyard on one coast with consumers on another. Thousands of pieces can reveal patterns, which regions supplied particular markets, when those connections intensified, when they declined, and how far a commodity traveled. In some places, the discarded containers themselves accumulated into monuments. Rome's Monte Testaccio, for example, is an artificial hill largely composed of fragments from millions of amphorae, many associated with imported olive oil. The containers became waste. The waste became evidence of the scale of Mediterranean supply. By the time Rome came to dominate the basin, maritime connectivity had become inseparable from imperial power. Roman expansion did not create Mediterranean trade from nothing. Phoenicians, Greeks, Etruscans, Egyptians, and countless other societies had already been crossing these waters for centuries. Rome inherited, expanded, and increasingly organized networks that were already ancient. What changed was the scale at which one political system came to depend upon them. The Roman phrase mare nostrum, our sea, captures something of that shift in perspective. Rome eventually controlled territories surrounding enormous stretches of the Mediterranean. But military control meant little unless ships could move soldiers, taxes, food, and information between them. The empire was not held together by roads alone. The sea dramatically reduced the cost and difficulty of transporting large quantities of heavy cargo compared with moving the same goods over land. Nothing demonstrates that more clearly than grain. Ancient Rome became one of the largest cities the pre-industrial world had ever seen. A city of that scale could not reliably feed itself from the farmland immediately surrounding it. Vast quantities of grain had to arrive continuously from elsewhere. North Africa became enormously important, as did Egypt and other grain-producing regions at different times. Large merchant vessels carried grain across the Mediterranean toward Italy. At Ostia, and later the great harbour complex of Portus, cargo could be transferred to smaller vessels capable of moving up the Tiber toward Rome. The archaeological park at Ostia describes this system directly. Large merchant ships brought grain across the Mediterranean, after which it could be transferred into rivercraft for the final journey inland. This supply chain reveals a side of empire that marble monuments can easily hide. Rome's population depended on sailors it would never meet. A grain ship leaving Alexandria or a North African port carried more than a commercial cargo. It carried part of the food security of the imperial capital. A storm that destroyed enough ships could have consequences far beyond the families of the lost crews. Delayed harvests, piracy, war, or transport disruption could become political problems. The Roman state therefore developed institutions connected to the grain supply, while private merchants, ship owners, and contractors remained deeply involved. Large-scale maritime transport was not decorative prosperity. It was infrastructure. A ship loaded with grain also illustrates why the Mediterranean linked environments as well as civilizations. Grain grown with Nile water could feed someone in Rome. Spanish olive oil could travel east or north. Wine produced in one province could be consumed in another. Garum and other fish products moved between ports. Marble quarried from islands or coastal regions could be transported for temples, baths, and monuments far from the quarry. Metals, timber, ceramics, glass, and luxury products flowed through overlapping networks. The sea allowed landscapes to specialize. A region did not have to produce everything its population consumed if ships could bring the missing goods from somewhere else. That sounds ordinary in a modern global economy. In antiquity, it was transformative. Maritime connectivity allowed cities to grow beyond what their immediate surroundings might otherwise support. It gave armies access to distant supplies. It connected mines to workshops and farms to urban consumers. Political power increasingly depended upon keeping those routes usable. And because the Mediterranean touched 3 continents, the network never belonged to Europe alone. North Africa was central to it. Egypt was central to it. The Levant was central to it. Ports along Anatolia and the eastern Mediterranean connected maritime traffic with routes extending deep into Asia. Goods arriving at a Mediterranean harbour might have travelled far beyond the sea before reaching the coast. The Mediterranean was therefore not an isolated economic world. It functioned as one great junction within wider systems reaching into Africa, Arabia, Mesopotamia, and eventually much farther east. Ideas moved with those goods. The Phoenician writing tradition contributed to alphabetic systems that would profoundly influence Greek writing, and, through later developments, the alphabets used across much of the world today. Greek language and culture spread through settlement and trade. Later, Roman political institutions and Latin traveled around the basin, but they encountered societies with traditions far older than Rome itself. Religious beliefs crossed ports and changed as communities adopted and reinterpreted them. Egyptian deities acquired worshippers far from the Nile. Eastern cults appeared in Western cities. Christianity itself spread through an interconnected Mediterranean in which ships and established urban routes made travel between distant communities possible. Disease could follow the same paths. So could armies. Connectivity is not inherently peaceful. The routes that allowed merchants to exchange wine and metal also allowed fleets to invade. Control of strategic straits and harbours became a military objective precisely because the sea was so useful. The wars between Rome and Carthage were not struggles over meaningless water separating 2 powers. They were struggles occurring inside a shared maritime system both needed. Sicily became strategically crucial because of its location. Naval battles could change access to trade, territory, and supply. Piracy flourished where states could not control movement effectively. A ship's ability to connect worlds also made it worth capturing. Yet, political boundaries repeatedly changed, while many routes survived them. Ports conquered by one empire could continue operating under another. Sailors adjusted to new taxes, laws and authorities while still responding to the same winds and geography. The same island that served Phoenician traders could later receive Greek merchants, Roman officials, Byzantine sailors, Arab fleets, Venetian ships, and eventually modern ferries. Geography gave some places importance that outlived the governments controlling them. That continuity is why Mediterranean history can feel strangely compressed when viewed from the water. A modern vessel entering a harbour may follow a route known in some form for thousands of years. A lighthouse can stand near the remains of an ancient port. Fishing boats may cross above anchorages used by merchants whose languages disappeared centuries ago. The surface continually renews itself, erasing wakes within minutes, while human movement across it leaves long-lived consequences on shore, and sometimes beneath it. Every system built around maritime travel contains failure. Winds were misjudged, hulls leaked, cargo shifted, ships struck reefs, fire broke out, fleets collided in battle, sudden storms caught vessels too far from shelter. A captain who had successfully crossed the same route many times could still disappear on the next voyage. Most ships arrived. That is why Mediterranean civilization became so connected. But the ships that did not arrive created another kind of record. When a merchant vessel sank quickly enough, the seabed could preserve the shape of its final journey. Amphorae might remain stacked where the cargo hold once stood. Anchors could reveal attempts to save the ship. Ceramic forms could identify where it had loaded. Coins, tools, and personal belongings could narrow the date. Timber could reveal how the hull was constructed. Even when the wood eventually disappeared, The cargo could leave the outline of a vessel resting on the bottom. For thousands of years, those wrecks accumulated beneath routes still being used above them. The Mediterranean had become a highway. Its seafloor was becoming the archive of everyone who failed to reach the other side. The wrecks did not stop accumulating when Rome disappeared, and they had not begun when Rome rose. By the time Roman grain ships were crossing from North Africa toward Italy, vessels had already been moving through the Mediterranean for thousands of years. After them came Byzantine traders, Islamic fleets, Venetian and Genoese merchants, Ottoman vessels, warships, fishing boats, steamships, and eventually the steel hulls of the Industrial Age. Most completed their journeys and left little physical trace in the water. A wake disappears within minutes. A wooden ship that reaches harbour may eventually be dismantled, repaired beyond recognition, or burned. Cargo is unloaded and dispersed. The people aboard continue with their lives. But when a vessel sinks, that process can suddenly stop. A working ship becomes an archaeological site, sometimes in the space of a few minutes. That is what makes a wreck fundamentally different from an object displayed in a museum. A museum collection is usually assembled deliberately. A wreck is an accident that preserves association. Containers may remain where sailors stacked them. Anchors can lie near the bow. Cooking vessels, lamps, tools, and personal belongings may survive close to the people who once used them. The hull can preserve construction techniques never described in surviving texts. Even when wood disappears, rows of ceramic containers can retain the approximate shape of a cargo hold that vanished centuries ago. Archaeologists are not simply finding old things underwater, they are finding relationships between things. Consider a merchant vessel carrying amphorae. From the surface, there is nothing remarkable about the water above it. Centuries pass, storms cross overhead, empires change. Modern ships may unknowingly travel across exactly the same position. On the bottom, however, the cargo can remain concentrated within an area only a few tens of meters long. Some amphorae break during the sinking. Others settle into sediment intact. Their organic contents usually disappear, although residues can sometimes survive. Marine organisms grow over exposed surfaces. Sediment gradually covers lower layers. To an archaeologist arriving 2,000 years later, the pile is not random pottery. The form of an amphora can provide clues to where and when it was manufactured. Clay composition can sometimes narrow its geographical origin further. Stamps and painted inscriptions may identify producers, contents, or officials. Residue analysis can reveal what a container once held. A concentration of one amphora type beside smaller numbers of another can begin reconstructing a cargo. Combine that information with the wreck's location and approximate date, and an ancient commercial journey starts reappearing. The ship may have vanished, its route has not. Few places demonstrate this more clearly than the waters between Sicily and Tunisia. The Strait of Sicily sits almost exactly where the geography of the Mediterranean forces different worlds toward one another. To the east lie the Ionian Sea, Greece, the Levant, and Egypt. To the west lie Sardinia, the Tyrrhenian Sea, Iberia, and the route toward Gibraltar. To the north is Sicily, and beyond it the Italian peninsula. To the south lies North Africa. Ships moving between these regions repeatedly crossed the same central corridor, and inside that corridor is the Scherchi Bank. Its location made it useful. Its geology made it dangerous. Scherchi consists of shallow banks and reefs in a region otherwise crossed by major maritime routes. In places, rocky hazards rise to less than a meter below the surface. A sailor can therefore be surrounded by apparently open Mediterranean water while approaching a reef capable of tearing into a hull. UNESCO describes the area as both one of the Mediterranean's historically busiest routes and one of its most perilous, with wrecks accumulated there for more than 3,000 years. That combination, heavy traffic and hidden danger, turned part of the seabed into an accidental archive. Ancient vessels crossed here while moving between Rome and Carthage. Later ships followed routes between Europe and North Africa. Military fleets passed through during wars separated by centuries. Modern vessels still use the corridor. The importance of Skerki is therefore not that one legendary ship sank there. It is almost the opposite. Different ships from different societies carrying different cargoes were lost within the same geographical bottleneck. Researchers were already beginning to understand that extraordinary concentration by the late 20th century. American deep-sea expeditions between 1988 and 1997 explored areas north of the bank and located at least 8 well-preserved wrecks from different periods. Those missions became important, early examples of archaeological work in deep water, where conventional diving was impossible or severely limited. UNESCO later identified 5 Roman wrecks in the wider Skerki archaeological record, dating between roughly the 1st century BC and 4th century AD. The wrecks transform the historical trade network we followed earlier from an abstraction into something physical. A historian can tell us that wine moved around the Roman Mediterranean. An amphora on a wreck can show us one shipment of it. One particularly revealing example appeared during a major international mission in 2022. Archaeologists surveying the Tunisian continental shelf documented a wreck designated SK3, lying at approximately 65 meters depth. The site was interpreted provisionally as a merchant vessel about 15 meters long and 5 meters wide, dating from approximately the end of the 1st century BC to the middle of the 2nd century AD. Its visible cargo included Dressel 2-4 amphorae, containers widely associated with the transport of wine. UNESCO's preliminary documentation therefore lists wine as the likely cargo, while correctly keeping the identification cautious. That caution matters. Archaeology becomes less interesting, not more, when uncertainty is replaced with invented certainty. Nobody needs to pretend that SK3 carried treasure or belonged to a famous captain. A 15-meter merchant ship carrying amphorae is already an extraordinary thing to find because it represents ordinary Mediterranean life. Somewhere around 2,000 years ago, people loaded those containers onto a vessel, expecting them to arrive somewhere else. Sailors prepared for a journey they considered survivable. Someone financed the cargo. Someone expected to sell or receive it. The ship entered a commercial network connecting farms, workshops, ports, and consumers. Then the journey ended at Skerki. The transaction failed. The archaeological record survived. Nearby wrecks tell entirely different stories. The same 2022 work documented 2 other sites on the Tunisian shelf, interpreted as much more recent vessels, probably from around the late 19th or early 20th century. One was a large metal wreck, approximately 74 meters long. Another appeared to be a smaller wooden vessel, perhaps a fishing boat. The contrast is precisely what makes the area so powerful. A Roman merchant ship and industrial-era vessels can occupy the same underwater landscape because the geography that mattered to sailors persisted long after the political world above had changed. And Skerki's archive reaches into warfare as well. The region was the scene of a naval battle in December 1942 during the Second World War. UNESCO's records also note the wreck of HMS Athenienne, lost on the banks in 1806, after a career that had taken the vessel as far as China. More than 300 people died with the ship. Ancient commerce, 19th century naval history, and 20th century warfare overlap within the same corridor. There is no need for Atlantis here. The real seabed is more useful than the myth because it contains evidence rather than possibility. Finding that evidence, however, is difficult. Archaeologists cannot simply descend and wander across hundreds of square kilometers looking for pottery. Deep water archaeology increasingly begins the same way modern oceanography does, with sound. A research vessel can survey the bottom using multi-beam sonar, sending acoustic pulses downward and measuring their return. The resulting bathymetric map reveals the shape of the seabed at high resolution. Anomalies can then be investigated more closely. Side-scan sonar can produce image-like acoustic views in which a wreck may appear through its shape and the shadow it casts acoustically. Magnetometers can help identify concentrations of ferrous metal. The objective is not immediately to recover objects. First, researchers need to know what is there. The 2022 UNESCO mission demonstrated how different this has become from the image of an archaeologist in scuba gear brushing sand from an amphora. Scientists from Algeria, Croatia, Egypt, France, Italy, Morocco, Spain and Tunisia spent 14 days aboard the French research vessel Alfred Merlin. More than 20 researchers and specialists participated. 2 remotely operated vehicles investigated sites below the ship. One of them, Arthur, was designed specifically for deep archaeological surveys and worked at depths of roughly 700 to 900 meters on the Italian continental shelf. Across the expedition, researchers collected more than 400 hours of video and over 20,000 photographs. On the Skirky Bank itself, multi-beam surveys covered approximately 10 square kilometers. The robots changed what could be examined. A human diver has strict depth and time limitations. An ROV can descend hundreds of meters, while its pilots remain aboard the research vessel. Cameras transmit the site upward. Lights illuminate objects that may not have been seen since the vessel sank. Manipulator arms can inspect or sample when appropriate. Scientists from different disciplines can watch the same feed simultaneously. And instead of bringing an entire wreck to the surface, archaeologists can increasingly bring a detailed digital version of it back. Photogrammetry uses many overlapping photographs of the same site from different positions. Software identifies common points between images and reconstructs the geometry in 3 dimensions. The result can be an extraordinarily detailed model of a wreck as it lies on the seabed. An archaeologist can later examine the distribution of amphorae, measure objects and compare parts of the site without physically disturbing them. UNESCO's 2022 expedition specifically gathered imagery for photogrammetric processing of previously known wrecks and produced high-resolution documentation across sites ranging from antiquity to the 19th century. That ability is especially important because a shipwreck is not valuable merely for what can be removed from it. Its position is information. Move an amphora without recording where it came from, and part of the story disappears. Remove every attractive object and leave only broken fragments, and the site becomes harder to interpret. Looting, therefore, destroys knowledge even when the stolen artifacts survive in private collections. UNESCO has specifically identified past looting by amateur divers as one of the threats to wrecks around Skirky, alongside fishing and trawling impacts. Sometimes the best preservation is simply leaving a site where it is. Underwater conditions can protect archaeological material in ways that initially seem counterintuitive. Sediment can rapidly bury parts of a wreck, limiting physical disturbance and sometimes creating low oxygen conditions that slow certain forms of decay. Ceramic survives particularly well. Stone and metal can remain recognizable for centuries, though metals corrode. Wood preservation varies enormously with burial conditions, biological activity, oxygen, and chemistry. In favorable anoxic sediments, structural timbers can survive far longer than exposed wood would on land. Depth can provide another kind of protection. A wreck hundreds of meters below the surface was effectively inaccessible for most of human history. No ancient salvage diver could reach it. Waves could not directly disturb it. Modern bottom trawling can still damage deep sites, and advanced technology has made previously inaccessible wrecks reachable, but deep water can preserve an archaeological snapshot with remarkable integrity. The Mediterranean contains other kinds of underwater archives as well. Harbors can sink or become partially submerged because of earthquakes, land subsidence, and long-term changes in relative sea level. Ancient waterfront structures now sit beneath modern waterlines. At places such as Alexandria, archaeological investigations have documented submerged structures and artifacts associated with the ancient city and its harbor zone. Elsewhere around the Mediterranean, Roman harbor installations, quays, fish tanks, and coastal structures preserve evidence of shorelines different from those of today. Sometimes entire portions of coastal settlements end up underwater, but again, the explanation is more interesting when we resist turning every submerged ruin into a lost civilization. Earthquakes lower land, coasts subside, storms alter shorelines, harbors are abandoned and silt over. sea level changes. Humans build repeatedly on top of earlier structures. The Mediterranean does not require a single dramatic sinking continent to produce submerged archaeology. Thousands of local geological and historical processes, operating over thousands of years, are enough. And because the basin has been so densely connected for so long, the quantity of material potentially remaining underwater is enormous. Each wreck captures only one interrupted journey, but together they allow archaeologists to reconstruct systems. Amphora distributions reveal trade. Hull remains reveal shipbuilding traditions. Anchors reveal maritime technology. Cooking equipment provides clues about life aboard. Personal objects remind us that cargo did not move itself. Coins can help establish dates. Animal bones and botanical remains can reveal provisions. Inscriptions can occasionally provide names. One ship can become a remarkably detailed sample of an economy. Hundreds of wrecks become something larger. They become traffic. That is what Skirky ultimately represents. The wrecks are not important only because ships sank there. They are important because so many ships passed there that losses accumulated across radically different historical periods. The seafloor records the persistence of a route. Above them, almost everything changed. Carthage fell, Rome expanded and fragmented. Religions transformed the political landscape. New languages spread around the coasts. Sailing vessels gave way to steam. Wood gave way to iron and steel. Navigation moved from stars and coastal memory to chronometers, radio, radar, and satellites. Yet vessels continued crossing between Sicily and North Africa because the Mediterranean's geography remained useful. For most of that history, humans adapted themselves to it. We waited for favorable winds. We sailed around continents. We stopped at islands because they were there. We built ports where coastlines offered shelter. We accepted Gibraltar as the western entrance and the long journey around Africa as the route between the Mediterranean and the Indian Ocean. Then, in the 19th century, that relationship changed. Engineers looked at the narrow land separating the Mediterranean from the Red Sea and decided that ships should no longer have to accept the geography they had inherited. For the first time in the story we have been following, one of the Mediterranean's most important gateways would not be opened by tectonics, erosion, or an ancient flood. Humans would dig it themselves. When the Suez Canal opened on 17 November 1869, its purpose was straightforward: shorten the maritime route between Europe and Asia. Until then, a ship traveling from the Mediterranean toward the Indian Ocean had to leave through Gibraltar, turn south into the Atlantic, and continue around the entire African continent before reaching waters that lay, on a map, only a narrow strip of desert away from Egypt. Engineers had spent years turning that strip of land into a navigable corridor. There were no locks separating the two seas. Ships could enter at Port Said on the Mediterranean coast, travel south through a sequence of excavated channels and natural depressions, cross the Bitter Lakes, and eventually emerge into the Gulf of Suez and the Red Sea. The canal changed the economics of global shipping almost immediately. What nobody designing it could fully appreciate was that ships would not be the only things to use the new route. For millions of years, the Mediterranean and Red Sea had belonged to different biological worlds. The Red Sea opened toward the Indian Ocean and supported warm-water Indo-Pacific communities. The Mediterranean, by contrast, had been repopulated largely from the Atlantic after the Messinian Salinity Crisis, and later shaped by repeated climatic changes and its narrow Atlantic gateway. The distance between them was small in geographical terms, but for marine organisms, the dry land of the Isthmus of Suez had been an absolute barrier. A fish cannot migrate across a desert simply because another sea lies on the other side. The canal removed that barrier. At first, the consequences were not obvious. The early Suez Canal was narrower and shallower than it is now. It passed through highly saline lakes, especially the Bitter Lakes, whose extreme conditions initially acted as a partial biological filter. A species moving north from the Red Sea had to tolerate the canal's salinity, temperature, and habitat before it could reach Mediterranean water. Nevertheless, organisms began making the journey. Fish appeared. Mollusks arrived. Crustaceans, worms, algae, and other forms of marine life followed. Some moved in the opposite direction, but the overwhelming ecological story became movement from the Red Sea toward the Mediterranean. The process eventually acquired a name, Lessepian migration, after Ferdinand de Lesseps, whose canal project had created the connection. Modern researchers regard it as one of the most important human-driven marine biogeographic changes taking place anywhere in the world. Estimates have changed as records improve and taxonomic uncertainties are resolved. But recent scientific reviews place the number of alien species reported from the Mediterranean at around 1,000, with the Suez Canal responsible for a large proportion of introductions, particularly in the Eastern Basin. The direction of that migration tells us something about the two seas. The Eastern Mediterranean is warm, saline, and comparatively poor in nutrients. The Red Sea is also warm, saline, and oligotrophic. Many Red Sea organisms therefore arrive already adapted to conditions that resemble those they encounter after moving through Suez. That does not mean every Red Sea species succeeds. Most biological introductions fail somewhere along the way. An animal may reach the Mediterranean but never reproduce. A few individuals may establish a population that remains small for decades. Others find a combination of temperature, habitat, and available food that allows them to spread with extraordinary speed. Rabbitfish provide one of the clearest examples of what happens when successful colonization begins changing the landscape itself. Two species, Siganus rivulatus and Siganus luridus, entered the Mediterranean from the Red Sea and became abundant across parts of the Eastern Basin. In their original tropical environments, rabbitfish are herbivores feeding heavily on algae. That same feeding strategy came with them. On Mediterranean rocky reefs, they graze repeatedly across algal communities that had evolved with a different assemblage and intensity of herbivorous fish. The result can be visible even to a diver who knows nothing about invasion biology. A healthy Mediterranean rocky reef may support thick stands of large brown algae, structures that function almost like underwater forests. Small animals shelter among them. Juvenile fish use them as habitat. They contribute primary production and create physical complexity above otherwise bare rock. Where rabbitfish grazing becomes intense, those forests can be stripped away. Research in the Eastern Mediterranean has documented transitions towards so-called barrens, rock surfaces with greatly reduced erect algal cover. Experimental work confirms that invasive rabbitfish can exert strong grazing pressure and reduce both algal production and habitat complexity. The change is much larger than replacing one fish with another. Remove the algal canopy, and organisms that depended on its shelter lose habitat. Nursery areas become simpler. The types of food available change. Species that thrive on open rock may increase, while forest-associated organisms decline. The architecture of the ecosystem has been altered by the feeding behavior of animals whose ancestors could not have entered this sea before 1869. Yet the story becomes even more interesting when predators are added. Researchers studying rabbitfish in Israel noticed that protected areas with more large predatory fish sometimes retained greater algal cover even where rabbitfish remained abundant. Experiments later found that rabbitfish exposed to chemical alarm cues from recently killed members of their own species reduced their feeding. The result hints at something important. Healthy predator populations may influence an invader not only by eating it, but by changing how confidently it feeds. An introduced species enters a food web, and the rest of that food web may determine the damage it can cause. Another newcomer announces itself far more dramatically. Lionfish are almost impossible to mistake for native Mediterranean fish. Their striped bodies are surrounded by long, thin rays carrying venomous spines, giving them an appearance more often associated with tropical reefs. The species spreading through the Mediterranean is principally Pterois miles, native to the Indian Ocean and Red Sea region. Sporadic Mediterranean records appeared decades ago, but a major expansion became evident during the 2010s. Populations established around Cyprus and the Levant then spread through portions of the Aegean and Ionian regions. By 2024, researchers reviewing Mediterranean records described an invasion front that had advanced considerably westward and northward from its initial eastern strongholds. Lionfish are effective predators. They approach small fish and crustaceans with a combination of camouflage and unusual hunting behavior, using their broad fins to corner prey before striking rapidly. In ecosystems where potential prey do not recognize them effectively as predators, they can have an additional advantage. The concern in the Mediterranean is not merely that another species has been added to the list. Lionfish may consume native fishes and crustaceans, compete with native predators, and alter reef communities if densities become sufficiently high. Their venom also changes the relationship between invasive species and people. Fishermen handling unfamiliar catches can be injured by the spines. Divers may encounter animals that were virtually unknown in these waters within living memory. In Cyprus and other eastern Mediterranean regions, removal programs have experimented with targeted culling and attempts to create commercial demand for lionfish meat. Once a marine predator has spread across international waters, eradication becomes nearly impossible. Management shifts from preventing arrival to reducing local effects. A fisherman pulling up a silver-cheeked toadfish faces a different problem. Largocephalus scleratus, often called the silver-cheeked toadfish or pufferfish, entered from the Red Sea and spread rapidly through the Mediterranean after being recorded in the early 21st century. It contains tetrodotoxin, a potent neurotoxin concentrated especially in some tissues and capable of causing severe poisoning if the fish is eaten. Its strong beak-like teeth can also damage fishing gear and bite through catches caught in nets or on lines. What might appear to be simply another unusual fish, therefore produces direct economic and public health consequences along parts of the coast. Greek assessments now list it among the country's significant marine invasive species. Jellyfish reveal yet another route from ecological change to everyday human experience. The nomad jellyfish, Rhopalema nomadica, originated in the Indo-Pacific and entered the eastern Mediterranean through the Suez Canal. Large seasonal swarms have occurred along Levantine coasts, sometimes interfering with beaches, fishing operations, and coastal infrastructure. Jellyfish blooms can clog intake systems that draw seawater for industrial facilities, while their stings turn an ecological invasion into something swimmers experience directly against their skin. No single species tells the entire story because most Lesepsian migrants are far less conspicuous. There are mollusks living among rocks, crustaceans in sediments, worms, algae, small fishes and microscopic organisms. Some have little measurable impact. Others provide new prey for native predators or become commercially valuable. Alien does not automatically mean destructive. Invasion biology distinguishes between a species introduced outside its historical range and an invasive species producing significant ecological or socio-economic effects. Treating every newcomer as equally harmful obscures the species that actually transform ecosystems. But viewed together, the newcomers have changed the biological identity of the eastern Mediterranean. Surveys along the Levantine coast have recorded communities in which alien fishes form a major portion of catches and local biomass. Some species that would once have immediately identified a fish market as Mediterranean now sit beside animals whose evolutionary origins lie in the Red Sea and Indo-Pacific. To an older fisherman, that change has taken place within one career. To geology, it happened almost instantaneously, and the canal itself has not remained the same. The waterway opened in 1869 was only the first version. Navigation demands led repeatedly to deepening, widening, and modification. Larger vessels needed more space. Traffic increased. Sections were expanded, including major modern projects that increased the canal's capacity. From a commercial perspective, every enlargement makes sense. From a biological perspective, reducing physical restrictions can also make the corridor easier for organisms to cross. Researchers have therefore argued that continued enlargement has strengthened the Suez pathway even as climate change makes the Mediterranean increasingly suitable for warm water arrivals. This interaction between the canal and temperature may be more consequential than either factor alone. A tropical species can reach a new sea and still fail if winter becomes too cold. Temperature acts as another barrier, but Mediterranean waters have been warming, particularly in the eastern basin. As minimum temperatures rise, regions that once excluded warm-adapted species can become survivable. Existing Lesepsian populations may spread farther north or west. New arrivals may establish more easily. A canal supplies potential colonists. Warming increases the amount of suitable habitat waiting for them. Recent reviews describe this combination as part of a wider tropicalization of the eastern Mediterranean. Rabbitfish illustrate the pattern again. They first became characteristic of the warmer eastern Mediterranean, but warming conditions have helped thermophilic species extend into regions that once formed stronger climatic barriers. Lionfish have similarly expanded beyond their early eastern Mediterranean range. This does not mean the entire basin will simply turn into a copy of the Red Sea. Local habitat, currents, predators, fishing pressure, and competition all determine which organisms succeed. But the species composition of the Mediterranean is already moving towards something that did not exist before humans opened Suez. The canal is also only one route. Every cargo ship entering the Mediterranean can potentially carry organisms with it. Ships have historically taken ballast water into tanks to stabilize themselves when cargo conditions change. That water contains microscopic life, plankton, larvae, bacteria, and small animals, from the port where it was collected. When ballast is discharged somewhere else, those organisms are released into a new environment. The International Maritime Organization treats ballast water transport as a major pathway for aquatic invasive species, and has specific international rules intended to reduce the risk, including requirements for ballast water management and treatment. The Mediterranean's intense shipping network makes that issue especially important here. Other organisms travel attached to the ships themselves. Barnacles, mussels, algae, bryozoans, and countless smaller creatures can settle onto hulls, propellers, sea chests, and other submerged surfaces. A vessel becomes a moving, artificial reef. When it reaches another harbor, organisms may reproduce or detach. Recreational boats and yachts can move species between Mediterranean marinas after an initial introduction, spreading them around the basin in smaller steps. Regional Mediterranean guidance has long recognized hull fouling alongside ballast water as an important introduction pathway. Shipping can therefore change biology in two very different ways at once. The Suez Canal creates a permanent geographical corridor through which organisms can migrate under their own power or through normal dispersal. Ships themselves act as vehicles capable of carrying organisms across barriers they could never cross naturally. The irony is difficult to miss. Mediterranean civilizations spent thousands of years becoming better at moving themselves across the sea. The Phoenicians improved ships, Greeks established distant colonies, Rome organized vast shipping networks. Industrial vessels eventually crossed entire oceans. With each technological improvement, humans became better at transporting other species too, sometimes intentionally. Aquaculture has introduced species for farming. The aquarium trade has released organisms accidentally or deliberately. More often, the passengers were never noticed. A lava in ballast water has no concept of global trade. A barnacle attached to a hull has no destination. A fish passing through Suez is not invading another country. Each simply responds to the opportunities created by a changing environment. The larger transformation emerges from millions of such individual events. This is why 1869 occupies such an unusual place in Mediterranean natural history. The Messinian Gateway Crisis had been driven by tectonics. The Zanclean reconnection had been opened by geology and erosion. Gibraltar's modern exchange is maintained by the shape of continents and the balance between evaporation and incoming Atlantic water. Suez was different. Humans looked at the map and edited it. We removed a land barrier that had separated marine ecosystems on evolutionary timescales and replaced it with open water. Nothing in the engineering plans needed to mention rabbitfish, lionfish, or jellyfish for their futures to be altered. A commercial shortcut became an ecological experiment spanning an entire sea, and that experiment is still running. Along the eastern Mediterranean, reefs are being grazed by herbivores whose ancestors came from the Red Sea. Fishermen encounter toxic pufferfish that were absent from their grandparents' catches. Divers photograph lionfish in places where the species did not exist a few decades earlier. Warm water organisms continue moving into environments that are themselves getting warmer. Suez opened the door, but what determines how far those species can walk through it is increasingly changing everywhere else in the Mediterranean. Water temperatures are rising. Marine heat waves are becoming more important ecological events. Some native organisms are being pushed beyond conditions under which their populations developed. Ancient seagrass meadows face combinations of warming, coastal development, and physical disturbance. Fisheries are adjusting to new species while old ones change distribution. The Mediterranean is no longer changing only on the geological timescale that created its mountains, trenches, and buried salt. Some of its most important transformations can now be watched within a human lifetime. Suez opened a door, but the sea itself is now changing around that doorway. A species arriving from the Red Sea still needs the right temperature, habitat, and food before it can establish a population. For much of the last century, those conditions placed limits on how far many warm water newcomers could spread. The eastern Mediterranean provided the easiest foothold. Farther north and west, winters could still become cold enough to slow or prevent expansion. That barrier is becoming less dependable. The Mediterranean has been warming through the water column, and extreme periods of unusual heat are no longer rare curiosities recorded at one coastal station. They have become basin-wide ecological events capable of affecting organisms from the surface down to communities attached permanently to the seabed. Recent analyses identify the Mediterranean as a major marine heatwave hotspot, and 2024 stood out as an exceptional year, particularly in the eastern basin, for the number and duration of marine heatwave days. A marine heatwave is not simply a hot afternoon at the beach. It is a period when seawater remains unusually warm compared with the normal conditions expected in that place and season. That distinction matters because marine organisms live inside the temperature, not beside it. A person can leave the water, find shade, or turn on air conditioning. A gorgonian fixed to a reef cannot move somewhere cooler. A seagrass meadow cannot migrate 20 kilometers north during a hot week. An animal may tolerate a short temperature spike that becomes dangerous when it continues for days or weeks. And because the Mediterranean contains species already living close to their upper thermal limits, a few additional degrees maintained long enough can turn stress into mortality. The sea also has memory. Water stores heat far more effectively than air. A hot atmospheric episode can transfer enormous amounts of energy into the upper ocean, especially when skies remain clear and winds weaken enough to reduce mixing with cooler water below. Research on the largest Mediterranean summer marine heatwaves has found that persistent subtropical high-pressure systems and weakened prevailing winds can create precisely those conditions. The surface absorbs heat while the usual mechanisms that remove or redistribute it become less effective. Once warm water extends deeper, the animals living tens of meters below the surface may lose the refuge that depth would normally provide. That became painfully clear during repeated warming events across the western Mediterranean. Divers returning to familiar reefs began seeing organisms they had known for years dying across large areas. Gorgonians, branching colonial animals that can create complex three-dimensional habitat on rocky reefs, were among the casualties. Sponges, corals, mollusks, and other organisms were affected as well. Research examining the period from 2015 to 2019 documented 5 consecutive years in which exceptional thermal conditions were associated with widespread mass mortality events around the Mediterranean. The phrase mass mortality can sound abstract until we picture what it means for an organism that may have taken decades to grow. A large Gorgonian colony does not rebuild itself the following summer in the way annual vegetation might return after a bad season. Some Mediterranean habitat-forming species grow slowly and recover slowly. When heat kills mature colonies across a reef, the loss continues after the dead tissue disappears. Small fish and invertebrates lose structure. Other organisms lose surfaces on which to settle. The reef still exists physically, but part of the architecture of the community has been removed. A heat wave can therefore leave an ecological footprint far longer than the weather event itself. And while some native organisms are being pushed toward their limits, species adapted to warmer environments are encountering the opposite situation. The canal brought rabbitfish, lionfish, pufferfish, and many other organisms into the Mediterranean, but warming helps determine where some of them can survive once they arrive. Recent scientific reviews describe the Eastern Mediterranean as both a climate change hotspot and a bioinvasion hotspot, with around 1,000 alien species reported and many warm-adapted migrants arriving through Suez. The combination is changing the meaning of a Mediterranean fish community. A fisherman does not need to read a temperature record to notice the shift if species once considered unusual begin appearing regularly in catches. The same process is occurring even farther west. Studies of fish communities in Spanish Mediterranean waters now examine tropicalization, the gradual increase of warm water species, and decline or displacement of colder affinity species as something measurable rather than hypothetical. The Mediterranean is not becoming tropical everywhere, and that word should not be interpreted as a prediction that its ecosystems will simply turn into Red Sea reefs. The change is uneven. Local currents, depth, habitat, fishing, and winter temperatures still matter. But the biological map is moving. That movement reaches fisheries directly. Every fishing tradition is built partly on expectation. A boat leaves harbour because generations of experience have established that certain animals appear in certain places during certain seasons. Warming disrupts those assumptions. Some fish move toward deeper or cooler water. Warm affinity species expand. Invasive blue crabs and other newcomers become significant enough in some regions to affect catches and fishing gear. The exceptionally long Mediterranean marine heatwave of 2023 was linked in Italian waters with changes involving invasive species and fisheries, illustrating how temperature and biological invasion can interact rather than operating as separate pressures. None of this means every change is a loss. Some fishermen gain new marketable species. A warmer water fish may become commercially useful where another stock declines. Ecosystems have always changed. What is unusual is the speed and the number of forces arriving together. Warming, intense fishing pressure, coastal construction, pollution, shipping, biological invasions and habitat loss, all acting on the same relatively enclosed sea. The coastline makes those pressures especially concentrated. The Mediterranean's edges have been desirable places to live for thousands of years, but modern development operates at a scale ancient harbour builders could never approach. Cities, marinas, hotels, roads, industrial areas and artificial beaches alter shorelines. Dredging changes sediment movement. Anchors scar the seabed. Wastewater adds nutrients and contaminants in places where coastal ecosystems evolved under different conditions. Rivers have been dammed, reducing sediment reaching some deltas and coastlines. At the same time, global sea level is rising as land ice melts and seawater expands as it warms. Around the Mediterranean, that global signal interacts with local subsidence, uplift, currents, and coastal geology, meaning the future waterline will not move identically everywhere. Regional assessments identify sea level rise, warming, and acidification among the major climate pressures affecting Mediterranean marine and coastal systems. For low-lying deltas, beaches, wetlands, and ancient coastal sites, even gradual sea level rise matters, because coastlines are balances between water, sediment, and land elevation. A sandy beach cannot simply move inland if a road, hotel, or seawall blocks its path. A wetland cannot migrate naturally if urban development occupies the ground behind it. The problem is therefore not only that the water rises, it is that many Mediterranean coasts no longer have enough freedom to respond. Beneath that rising surface, another chemical change is taking place. The The ocean absorbs a portion of the carbon dioxide released into the atmosphere. When carbon dioxide dissolves in seawater, it alters carbonate chemistry and lowers pH, a process known as ocean acidification. The Mediterranean is part of that global phenomenon. The exact biological consequences vary enormously between organisms and environments, but calcifying species that build shells or skeletons from calcium carbonate are among those researchers monitor closely. Acidification does not mean the Mediterranean is becoming an acid in the everyday sense. It means seawater is shifting toward lower pH than it previously had, changing the chemical environment in which marine organisms build and maintain their structures. Even the deep water circulation we followed through Gibraltar cannot be treated as permanently fixed. Temperature and salinity determine water density. Density helps determine where Mediterranean waters sink. Change temperature, evaporation, rainfall or salinity enough, and the characteristics of newly formed deep water can change with them. Observations have already documented substantial reorganizations of eastern Mediterranean deep water formation in recent decades, while studies of dissolved oxygen show that the processes controlling oxygen enrichment and depletion have also varied. Researchers do not expect the Mediterranean simply to stop overturning tomorrow. Modeling has suggested that deep oxygenation may be comparatively resilient even under large circulation changes. But the important point is that the currents described earlier are not machinery bolted permanently into place. They are produced by physical conditions, and those conditions can shift. To see what all these pressures mean on a more intimate scale, we can return to one of the least dramatic-looking organisms in the entire documentary. A ribbon of green leaves swaying beneath clear Mediterranean water, Posidonia oceanica. At first glance, it resembles ordinary seaweed. It is nothing of the sort. Posidonia is a true flowering plant whose ancestors returned to the sea after flowering plants had already evolved on land. It has roots. It produces flowers and fruits. Underground stems called rhizomes spread through the sediment, producing new shoots and allowing a meadow to expand clonally over time. The species is endemic to the Mediterranean. This is its only natural home. That makes a Posidonia meadow one of the most specifically Mediterranean habitats on Earth. Swimmers can pass directly over one without realizing how much is happening beneath them. Between the leaves live juvenile fishes, crustaceans, mollusks, and countless smaller organisms. Epiphytes grow on the leaf surfaces. Animals graze among them. The meadow slows moving water and traps suspended particles. Its roots and rhizomes help hold sediment in place, reducing erosion. Dead leaves accumulate below the living plants along with trapped material, slowly creating thick, organic-rich structures called mats. Those buried layers make Posidonia important in another way. Carbon captured during photosynthesis can become stored in the plant, and the sediments accumulated beneath the meadow. Because some of that organic material remains buried for long periods, seagrass ecosystems can function as significant stores of what is often called blue carbon. Posidonia, therefore, does not simply create habitat above the seabed. It changes the sediment underneath it, building a physical archive of biological activity over extremely long periods. And long is unusually appropriate here. Posidonia spreads clonally. Individual shoots are temporary, but genetically identical sections connected through rhizomes can persist and expand for extraordinarily long periods. Studies of genetic structure have suggested that some large clones may have persisted for thousands of years. Calling one of them an individual can become philosophically strange. Leaves die and are replaced. Rhizomes continue growing. Portions separate, yet the genetic lineage remains. A meadow beneath a modern resort may contain biological continuity older than many civilizations that rose around the Mediterranean. That longevity also makes rapid change especially uncomfortable. A system that took centuries or millennia to build can be damaged far more quickly. Anchors can tear rhizomes from the seabed. Coastal construction can bury or remove habitat. Pollution and excessive nutrient input can reduce water clarity, limiting the sunlight the plants require. Rising temperatures add another stress. Earlier modeling identified Mediterranean seagrass as vulnerable to regional warming, and more recent observations have shown that intense marine heatwaves influence Posidonia growth and reproduction. Yet Posidonia also produces one of the more surprising responses to heat. After extreme warming, flowering can increase dramatically. Researchers documented an exceptional basin-wide flowering event following the major marine heatwaves of 2022, with a 2026 analysis describing it as one of the strongest flowering events recorded for the species. That does not mean heat is beneficial overall. Stress can trigger increased sexual reproduction while simultaneously reducing vegetative growth. Earlier work found that shoots participating in flowering showed reduced rhizome production for at least 2 years afterward. What looks superficially like flourishing may actually represent a costly response to environmental stress. This is where the modern Mediterranean becomes difficult to interpret through simple categories. A warmer year can damage some organisms and allow others to expand. A newcomer can harm one habitat while becoming food or income elsewhere. A protected area can help predators recover and indirectly alter the behavior of invasive herbivores. A seagrass can flower spectacularly after a heat wave while paying a growth cost afterward. A circulation system can change without collapsing. A coastline can appear unchanged while the average waterline gradually moves upward. The sea is not transforming in one direction at the same rate everywhere. It is being reorganized, and for the first time in Mediterranean history, we can watch that reorganization with instruments capable of recording it nearly continuously. Satellites measure surface temperature from orbit, profiling floats descend through the water column, and return with temperature and salinity measurements. Tide gauges and satellite altimeters track sea level. Divers photograph permanent monitoring plots on reefs. Acoustic receivers detect tagged fish moving past underwater stations. Genetic analysis identifies species that would once have been difficult to distinguish. Fishing records reveal shifting catches. Automated sensors continue measuring after researchers return to shore. The modern Mediterranean is therefore observed more closely than any previous version of itself. That makes the speed of some changes impossible to dismiss as anecdotes. Recent decades have produced repeated marine heat waves, shifts in species distributions, and new combinations of native and introduced organisms. Some aquaculture regions of the Western Mediterranean show long-term warming trends extending through the water column, with particularly high rates at certain locations. And the sequence has continued. The Mediterranean experienced major thermal extremes in 2023 and 2024, followed by another severe marine heatwave affecting parts of the basin in 2025. For someone who began fishing or diving 40 years ago, this is not deep time. It is a career. A reef can change within the period one person has been visiting it. A species absent during childhood can become common by middle age. A fishing ground can begin producing animals previous generations rarely encountered. That is a fundamentally different kind of transformation from the one recorded beneath the Messinian salt. And yet placing the two beside one another changes the perspective. The Mediterranean has endured changes incomparably larger than anything humans have witnessed. It has lost much of its normal oceanic connection. It has accumulated immense evaporite deposits. Its water level has changed profoundly. Atlantic marine conditions returned. Tectonic movements built and destroyed gateways. Volcanoes appeared. Basins shifted. The difference is that those changes are measured in hundreds of thousands or millions of years. The transformations unfolding now can be detected between one scientific survey and the next. A Posidonia clone may have been growing before Rome existed, yet the seawater surrounding its newest leaves can become unusually hot within a single summer. A sperm whale follows a submarine canyon created by geological processes millions of years old, while ship noise passes through the water around it today. Rabbitfish move through a canal opened less than 2 centuries ago and graze reefs whose foundations developed long before humans appeared. At Calypso Deep, sediment accumulates records of ancient climate, while modern plastic settles onto the same bottom. Every timescale we have followed through this sea is now overlapping, but even the longest human record is brief compared with what comes next. The coastlines we recognize, the Strait of Gibraltar, the Aegean Islands, Sicily, the deep Hellenic trenches and the Mediterranean itself, are not the endpoints of geological history. Africa and Eurasia are still moving. Subduction continues, faults remain active, mountains are still being built and eroded. Basins that look permanent on today's maps occupy only one stage in a process that began long before the Mediterranean existed. For the final time, the clock has to widen. Not to the next summer, not to 2100, not even to the next civilization, to a future measured in millions of years, where the Mediterranean people know today becomes just another buried layer in the long history of a sea that has never remained the same. A small boat crossing the Mediterranean rarely looks as though it is traveling over anything complicated. From the surface, the sea still gives the same impression it has given for thousands of years. Open water, distant land, a horizon that hides more than it reveals. But after following this story from Gibraltar to the deepest trenches, from ancient salt to modern migration routes, that surface becomes almost impossible to see in the same way. Beneath one vessel moving eastward through Gibraltar, Atlantic water may be entering the Mediterranean near the surface, while denser, saltier Mediterranean water moves westward below it. That exchange is quiet enough to pass unnoticed, yet it compensates for a water deficit created every day by evaporation across the basin. The modern Mediterranean survives in its present form partly because this narrow gateway keeps moving water between two worlds. Far below that circulation lies the record of a time when the relationship failed. Buried beneath younger sediment are evaporites left by the Messinian Salinity Crisis, evidence that the Mediterranean once became so restricted that its chemistry, ecosystems and water levels were transformed. The salt does not tell us one simple story of a completely dry basin. It records something more complicated: repeated restriction, evaporation, changing water sources and environments unlike anything found across the Mediterranean today. Then the Atlantic connection returned. Whatever the exact speed and magnitude of the Zanclean refilling, the sea that emerged afterward entered a new chapter. Marine organisms returned. Sediments covered the old crisis. Rivers adjusted to higher water levels. The Mediterranean gradually became recognizable again. But the earth beneath it never stopped moving. South of Greece, African lithosphere continues descending beneath the Aegean region. Faults store strain. Earthquakes release it. Volcanoes such as Santorini and Stromboli remind us that some of the Mediterranean's most beautiful landscapes are temporary arrangements produced by active geology. Mountains rise because crust is being deformed. Trenches descend because parts of that crust are being consumed. Islands occupy places where geological processes reach the surface. The geography around the Mediterranean therefore looks permanent only because human lives are short. Travel into one of its deep canyons and another Mediterranean appears. Sunlight disappears. Pressure rises. Food becomes scarce. Sperm whales leave the atmosphere behind and descend into that darkness to hunt. Cuvier's beaked whales travel deeper still. At Calypso Deep, more than 5 kilometers beneath the surface, the seabed receives particles that began high in the water column, sediment transported through deep currents, and now even plastic carried from the human world above. The deepest part of the Mediterranean is not separate from its surface. Nothing really is. A microscopic plankton bloom can eventually feed a fish, a tuna, or a whale. A particle eroded from land can travel down a submarine canyon. A plastic bag dropped into the human Mediterranean can eventually settle into the abyss. A change in water temperature can alter which species survive hundreds of kilometers away. The same interconnectedness appears in shallow water. A Posidonia meadow growing only a few meters below the surface may look insignificant beside volcanoes, whales, and deep trenches. Yet it creates habitat, stabilizes sediment, stores carbon, and supports organisms that feed much larger food webs. Some of these meadows have persisted through periods in which entire civilizations appeared and disappeared around them. Above those meadows, people have been crossing the sea for thousands of years. Phoenician merchants learned routes between distant coastlines. Greek settlers turned islands into stepping stones. Roman ships carried grain, oil, wine, and people across a maritime system that helped sustain one of history's largest empires. What modern maps show as empty blue space became one of the most effective transportation networks of the ancient world. The sea did not isolate Mediterranean civilizations. It helped create them. And when ships failed, the bottom preserved pieces of those journeys. Amphorae still lie where cargoes came to rest. Ship timbers reveal construction methods. Anchors mark decisions made during emergencies no written source remembers. Around places such as Skirky Bank, vessels from different centuries occupy the same underwater corridor because the geography continued directing traffic long after the cultures using it had changed. Then humans altered that geography. The opening of the Suez Canal connected the Mediterranean directly with the Red Sea in a way that tectonics had not done for millions of years. The canal was built for ships, but fish, mollusks, crustaceans, and other organisms used it as well. Rabbitfish began grazing Mediterranean reefs. Lionfish appeared in waters where they had never existed before. Pufferfish entered fisheries. A boundary that evolution had maintained was replaced by a navigable corridor. And now the environment on the Mediterranean side of that corridor is changing too. The water is warming. Marine heat waves are becoming increasingly important ecological events. Some cold affinity organisms are losing suitable conditions. Warm water species are extending their ranges. Native species, introduced species, fisheries and coastal habitats are being reorganized together. The Mediterranean is not simply moving toward one predictable future. Different regions will respond differently. Some species may decline while others increase. Some habitats may recover where pressures are reduced. Others may struggle against combinations of warming, pollution, development, and biological invasion. That uncertainty is important because the Mediterranean has never followed a single straight path. Even the geological future is more complicated than a simple prediction that Africa will one day close the sea. Africa and Eurasia continue their relative convergence, but the Mediterranean region consists of smaller plates, subduction zones, rotating blocks, expanding basins, and active faults. Some regions are being compressed while others are stretched. Over millions of years, mountain ranges will continue rising and eroding. Oceanic crust will continue disappearing in some places. Existing basins may narrow, migrate, or be replaced. New gateways could form while others close. The exact map is unknowable. The direction is not. Today's Mediterranean is temporary. That may be the most important thing hidden beneath its surface. Not one lost city, not one mysterious creature, not one secret trench. The deeper story is that the Mediterranean has repeatedly changed what kind of place it is. Long before humans appeared, it was part of a much older marine world connected to the remnants of the Tethys Ocean. Later, it became increasingly restricted. During the Messinian Salinity Crisis, enormous quantities of salt accumulated while ordinary marine conditions broke down. Atlantic connectivity returned. The basin filled and marine ecosystems rebuilt. Tectonic forces continued reshaping the seafloor. Animals learned to exploit the currents, canyons, coastal habitats, and seasonal productivity created by that geography. Humans then turned the same sea into a network of trade, migration, and empire. Shipwrecks transformed parts of its bottom into archaeological archives. Industry connected it directly with another ocean. And within the last few generations, humanity has begun changing its temperature, chemistry, and biological communities at a speed that can be observed within a single lifetime. There has never really been one Mediterranean. There have been many. A geological basin, a salt-producing crisis, a refilled sea, a corridor for whales and tuna, a road between civilizations, a graveyard of ships, a laboratory of evolution and invasion, a heavily inhabited ecosystem now moving into another phase. The remarkable thing is that all of those versions occupy the same place. They are stacked through time. A modern ferry can pass above a Roman wreck. That wreck can lie on sediment deposited over Messinian salt. Beneath the salt, Older rock records worlds that existed before the Mediterranean had its present shape. Farther down, tectonic plates continue moving whether anyone is watching or not. And above all of it, life carries on. Whales surface. Turtles cross between nesting beaches and feeding grounds. Fishermen return to harbors. Cargo ships pass through Gibraltar and Suez. Tourists swim over seagrass meadows. Volcanoes release gas. Currents carry Atlantic water east and Mediterranean water west. Every layer of the story is still active somewhere. That is why the Mediterranean cannot really be understood by looking at a map. A map freezes geography. The Mediterranean is a process. It has been opening, closing, filling, evaporating, colliding, sinking, rising, migrating and connecting for millions of years. The blue surface people recognize today is simply where all of those processes happen to meet now, and beneath it lies the evidence that they will not remain arranged this way forever.